Assalamu alaikum. Good morning, everyone, and welcome to the second international webinar in science, sustainable development, and ecosystem in Saudi Arabia. First, my name is Thani Al-Qahtani, Assistant Professor of Materials in Physics Department at Abdurrahman bin Faisal University. I am very pleased to be your host in this session on advanced materials and the green chemistry of energy and water sustainability. Let's welcome first our first speaker, Prof. C.B. Chow. Tanning, he will speak about the tanning surface electronic structure of two-dimensional nanosheet through surface treatment for high-efficient water oxidation. Professor C.B. Chow received his bachelor degree in 1983 from Nanjing University, his master degree in 1989, and PhD in 1992 degree from University of Science and Technology of China. He was a postdoc fellow in Fion University during 1992 to 1994. Now he is a professor in the School of Material Science and Engineering at Beijing Institution of Technology. His research interests focus on energy-related material. He co-authored more than 370 peer-reviewed papers, obtained more than 40 patents. So welcome, C.B. Chow. Doctor, are you with us? Can you hear me?
Yes.
Yeah, can you please share your screen and welcome. Thank you for being with us today.
Okay.
Can you please, yes. Okay.
No.
Yeah,
you can see my
screen. Yeah, we can see your screen. Yes.
Okay.
You can start.
So, thank you for your introduction, Chair. My name is Chen Baocao, came from China, Beijing Institute of Technology. I want to thank the conference organization to give me the opportunity to present my talk. My talk title is Tuning Surface Electronic Structure of Two-Dimensional Nanosheets Through Surface Treatment for Highly Efficient Water Oxidation. My talk will follow the outline like this. First, introduction, and then enhance OER properties by surface modification on cobalt hydroxide. Then the nickel ion LDH treated by sulfate and enhance OER properties. And finally, a short summary. First, introduction. With the development of society, the consuming of the energy repeatedly demand. So this growing energy demands much more better energy conversion and storage materials. So water splitting is one of the methods to harvest electronic energy from renewable sources such as sun and wind, and converting it into chemical energy, the hydrogen. In this process, there is a oxygen evolution reaction exist in the process. That is the OER process. The OER also exists in fuel cell, mental air battery process, etc. So it is an important process was to study. The OER process involves a 4-protein coupled electron charge transfer states, it generally need catalysts to support this process. So the OER catalyst generally including noble mentor and their compound. The benchmark catalyst including ruthenium oxides and uranium oxide, but there are they have the large O potential and they have scarcity, etc. Drawbacks. So developing those abundant transition mentor-based materials as low-cost and efficient OER electrocatalysts is still a challenging task. The transition mentor-based materials such as hydroxide, oxide, etc. For example, the cobalt hydroxide, nickel iron, LDH has studied extensively, but the problem is still the improving catalytic efficiency. The way including increase the active area, produce defects, etc. Generally, they involve a complicated technology. So here, I want to introduce a method, a sample method, through surface modification to tuning surface electronic structure and improve the OER properties. Our work focus on the nanosheets. That is a two-dimension nanostructure, because unique ultra-thin two-dimension nanostructure can offer large surface area, short charge or mass diffusion passes, and abundant activity seeds. The next, I will introduce the work on in situ surface modification of cobalt hydroxides. We use a sample method, the microwave method, to produce materials, catalytic materials. Generally, we use cobalt nitride and ethylene glycol plus urea to produce alpha cobalt hydroxide. Similarly, we use the same precursor, but use the sodium hydroxide to replace the urine. We can obtain the beta cobalt hydroxide. But if we use a cobalt acetate to replace the cobalt nitride, partly replace, we can obtain the modified materials. That is in the alpha cobalt hydroxide, we can obtain the capsulate alpha cobalt hydroxide. As indicated by scheme picture, some of the capsulate replace the hydroxide group on the surface. And if we measure the phase structure, we can find that before or after the modification, there is no difference between the phase structure. And the thickness of the nanosheets is about 1 nanometer. We use FTIR spectrum to identify the structure change before and after the modification. We find that there is a new peak appear in the alpha cobalt hydroxide after the modification. This is correspond to the capsulate group. Similarly, there are 3 peaks appeared in the beta cobalt hydroxide. This corresponds to the acetic anhydride. So we can confirm that we obtained the modified structure. And when we observe the morphology, we can find that after and before the modification, there are no change of morphology. The morphology is a nanosheets, a transparent characteristic, and contains some porous structure. The element uniquely the element distributed formally on the surface. We have used a contact angle to measure the wettability to compare the wettability of before and after the modification. We find that before the modification, the contact angle is about 130, but after the modification, the contact angle decreased to 123. This means that the wettability increased. And we also have compared that after the catalytic reaction, the contact angle, we find that the unmodified sample, the contact angle is almost keep stable, but the modified sample, the contact angle has a remarkable decrease. This means that after the modification, the wettability increased and also beneficial to the oxygen absorbed on the surface. Now we measure the OER properties using LSV curves. We can find that from this curve, for alpha cobalt hydroxide, at the current density of 10, the O potential is about 309 millivolts. But after the modification, the O potential decreased to 288 millivolts. Similarly, for beta cobalt hydroxide, also the O potential decreased significantly. So this means that after the modification, both materials OER properties increased, enhanced. And if we measure the turnover frequency, this relates to the catalytic activities. If we compare the O potential at 300 millivolts, we can find that the TOF volume doubled after the modification. If we use a capacitance of double layer to measure the electronic chemical surface area, this relates to the area density of active states. We find that after the modification, the ECAC increased remarkably, for both materials. So this means that the OER properties enhancement due to the active states increased. And if we compare the tough slopes, we find that the situation is rather complicated. For alpha cobalt hydroxide, there is almost not so much change of the tough slope, but for beta, there is a significant change. This means that this data reflect the kinetic properties. So maybe the different function group has a different effect on the surface structure and process. The situation of the reflection resistant is also the similar with the tough slope. So it's rather complicated to explain different groups on the surface effect on the OER properties. We have also studied the concentration effect on the property. We find that there is an optimal concentration on the property. The optimal concentration is about 10% of reactant. And we have measured the stability. We find that there is a good stability of the property. And after the catalytic reaction, we can find that the morphology can keep nanosheets. And the filing efficiency can keep stable, even can increase after that surface modification. If we use the XPS measure the cobalt valence, we can find that compare the alpha cobalt and the modified alpha cobalt, capsulated alpha cobalt. We find that the peak position shifted about 0.8 eV. This means that before the modification, the cobalt belongs to cobalt 2, but after the modification, the cobalt became cobalt 3. So this means that the surface modification can effect on the cobalt valence. And also, if we measure the oxygen state, we can find that after the modification, the peak shape changed. If we feed the peak, we can find that after the modification, there are more oxidative effects produced in the materials. This is also indicate that the surface modification not only effect on the mental valence, but also on the oxygen state. So we then we use a DFT method to simulate the mental electron structure. We find indeed that there is a changes before and after the modification, and this can explain why the surface modification can tuning the electronic structure and then enhance the OER properties. And next, I will present the work on the nickel iron LGH nanosheets treated by sulfate. As we know, the nickel iron LGH is a well-known OER catalyst. Due to the nickel and iron's synergetic effect, it has a good catalytic properties. Previously, the theoretical research indicate that the nickel and iron has a high valence in the catalytic process. But in the experimental respect, how to realize the high valence nickel and iron is rather difficult. So here we use an in situ surface modification through ion exchange sulfate to realize the high valence nickel and iron. Similarly, we also use a microwave method to prepare the nickel iron LGH nanosheets, and then we use ammonium sulfate to treat the nanosheets to obtain the sulfated nickel iron LGH nanosheets. We use the ion exchange method to use a sulfate to replace the nitric groups between the layer. And if we measure the XRD structure, we find that only a slight shift of the peak indicate that after the ion exchange, the distance between the distance of the layer increased, and the thickness is also about 1 nanometer. But there are some places we can find that the 3 or 4 nanometers thickness. That means that the nanosheets maybe can stack together. And the TM also show that the transparent characteristic. We also may use the FTIR to conform the surface structure changes we find after the ion exchange, the structure changed. It appeared a sulfate peak. And if we use XPS, measure the nickel and the ions valence, we find after the ion exchange, the nickel peak position shifted about 0.2 eV. This is it means that the ion exchange produced the EV code on the nickel. Similarly, also that the ion peak shifted about 0.8 eV. So this ion exchange can effect on the structure of electronic structure of mentor. But we also found an interesting phenomenon that if we use the sodium sulfate to replace ammonium sulfate, although the FTIR still we confirm the ion exchange, but if we measure the mentor valence, we find there are no peak shape. So this means that although the sulfate replaced in the layer, but maybe no effect on the mentor structure. So this means that not only the sulfate effect on the mentor structure, but also the environment, maybe pH valence, will also have the effect on the structure. Now we study the OER properties use as we code. We find that also at the 10 current density of 10, we find that the pristine nickel ion LDH has at a time about 270 millivolts, but after the ion exchange, we can get a very small overpotential of 216 millivolts. So this means that this method can significantly enhance the OER properties. And we also have studied the concentration effect on the OER properties. We find that the best one is came from the sample of 0.005. So it has a different, if we factor on the overpotential of 270 millivolts, we can obtain the different current density, use different samples. And we also measured the ECAC, the electronic chemical surface area. We also find that after the ion exchange, the active area increased remarkably. This means that the ion exchange surface modification can enhance properties. And also here, the top slope, this related to the kinetical properties. We also find that after the modification, all samples has smaller top slope. That means that the kinetic properties also enhanced. And we also measured the stability of both materials, nickel ion LDH and the sulfate nickel ion LDH. We find that they both have good stability. And the Faraday efficiency is also the highest Faraday efficiency comes from this sample. And we want to further study the mechanical. We find that we use the CV code to study the two samples. We find that in the nickel ion LDH, if compared with the sulfated nickel iron LDH, the oxidation area smaller than this one. And we can calculate the electron transport for nickel atoms. For the nickel iron LDH, this electron transport for nickel is about 0.5. But for the sulfated nickel iron LDH, it increased to 1.86, near to 2 atoms, 2 electrons. So this means that the electron transport in the different material is different. And also we measure the Minter's valence. It finds that in the nickel iron LDH, the nickel, if we compare before and after the catalytic reaction, we find before the catalytic reaction, the nickel should be the nickel 2. But after the reaction, nickel became nickel 2 and nickel 3. The ratio of nickel 2 and nickel 3 is about 56 to 44. But if we measure the sulfated nickel iron LDH, we find that before the reaction, the nickel 2 and the nickel 3, it contained both nickel 2 and nickel 3. And the ratio of nickel 2 and nickel 3 is about 38 to 52. And after the reaction, the nickel 2 and nickel 3 ratio became 9.5% and 90.5%. So these two materials has a big difference between the Minter's valence. The latter has much more high valence of nickel. If we analyze the iron solution, we find the similar phenomena. For the nickel iron LDH, we find that iron before and after the reaction, it moved about 0.9 eV. This means that the iron from 2 to 3 valence. And for sulfated nickel iron LDH, we find before the reaction, it already became the iron 3. And after the reaction, it further moved to a 0.8 EV. It should be became iron 4. So we also use a DFT method to simulate the structure changes before and after the modification. We find that there's a big difference about the electron structure. So from here, we also can explain that why this material has the possibility to enhance the OER properties, and the nickel and iron became high valence. According to the above result, we proposed a process that after the modification, the nickel became nickel 3, and through the reaction, nickel 3 became nickel 4 OH, and also through a multi-electron transfer process became nickel 4 OH. So this is our finding that the surface modification can increase the high valence content and enhance the OER properties. So now finally we give a short summary. First, the in situ treatment could modify surface structure of two-dimensional nanosheets. The capsulated group in situ modification cobalt hydroxide, tuning the surface electron structure and enhance OER properties. The sulfate nickel ion LGH nanosheath, while ion exchange significantly enhance OER properties due to the formation of high valence nickel and iron. The method opened a new approach to improve OER catalytic properties. And finally, I want to thank the support of National Natural Science Foundation of China and my students and colleagues' collaborations. Thank you for your attention. That's my presentation.
Thank you very much for sharing your work with us. Now the time for the discussion. I think Dr. Iman have a question for you.
Good morning, Dr. C.B. Chow. Thank you very much for being with us today and also for sharing with us your interest results. Indeed, Dr. Chow, your work is on improving the catalytic efficiency by increasing the active area. So you use here the microwave method for performing an in situ substitution of the cobalt hydroxide in the 2D nanostructure sheets. So my question, Professor, during that procedures in situ, can you perform an in situ monitoring so that you can control the amount of the doping and not exceed the desired amount, and also control the size of the active zone? You can control in situ?
Control. I don't know if I understand you.
Monitor.
We can control the doping, the concentration, but there is a optimum concentration to enhance properties. So maybe we can obtain the optimal property through the controlling the different concentrations of modification reagent. But maybe if we control the different concentration, maybe the properties is also different. I don't know if I understand your question.
Sorry, my question is about in situ monitoring. In situ during the modification, do you control it? Do you can control it?
During I haven't understand what your problem. Can you pardon your repeat your question?
Okay, I will type it.
Please, Dr. Iman, you can type the question so Prof can read and then answer.
Okay.
Right. What? You repeat your question?
I will type it.
Professor, she's typing the question for you in the chat session, please.
I don't understand what question. Social monitor what?
The active zone.
Active zone. Active zone. That is the size of material. You mean this? Generally, we our nanosheath generally has about several hundred nanometer. Generally, we want to decrease the size of the materials, because if we decrease the size of material, the surface area will increase. So this beneficial to the increase active state. So generally, we don't want to increase the surface area, but decrease the size of the materials. It can control the size, and the surface. If you think that active seeds, it depends on the of course on the surface structure. So if the size we can control, but the active seeds is that's the problem we want to study. Okay, this I don't know if I have answered your question.
Yes.
Okay.
Thank you very much.
Thank you.
Okay, thank you for being with us today. Thank you. Our next speaker is Dr. Asma Sharif. She is Associate Professor at College of Science at Imam Abdul Rahman bin Faisal University, Saudi Arabia. She is an Associate Professor in Department of Chemistry, where she teaches different courses in chemistry. She was a previous fellow of the IPK program at Massachusetts Institute of Technology, US. She worked as a visiting researcher and conduct research with several universities worldwide. She has several publications and participated in major international conferences. Her research area are clean water and clean energy, corrosion inhibitors, and nanotechnology. And her speak today, or her talk today, will be in polarization of waste feedstock using the green synthesis approach. So welcome, Dr. Asma. Thank you for being with us today. And can you please share your screen? Dr. Asma, can you hear us?
Dr. Tahani.
Yes. Yeah, we can hear you. Can you please share your screen? Yeah, we can see your screen. You can start. Thank you.
Good morning, everyone. I am Asma Sharif, an Associate Professor at the Chemistry Department at Imam Abdul Rahman bin Faisal University. I am going to make a presentation on valorization of waste feedstock using the green synthesis approach. This is the outline of my presentation. First, I will introduce my research, including motivation and objective. Then briefly, I will go through some theoretical background that need to be brought up. After that, I will show and discuss different designs and experimental results as well. Finally, summary and future work. In the current climate of several global crises, namely climate change, chemicals, energy, and oil, the impact of green chemistry with respect to chemicals and biofuels generated from within a holistic concept of a biorefinery will be discussed here. Green chemistry provides unique opportunities for innovation via product substitution, new feedstock generation, catalysis in aqueous media, utilization of microwaves, and scope for alternative or natural solvents. The potential of utilizing waste as a new resource and the development of integrated facilities producing multiple products from biomass will be presented here. In the future, the commercial success of biofuels with consumer demand will depend on the availability of new green chemical technologies capable of converting waste biomass to fuel in the context of biorefinery. Thus, chemical manufacturing faces a degree of pressure at all stages in the life cycle or supply chain of chemical products as shown in this figure. A biorefinery can be considered to be an integrated unit that can accept various biological non-food feedstock and convert them into a range of useful products, including chemicals, energy, and materials. The challenge is to use green chemicals technologies to ensure maximum conversion efficiencies and minimal waste so that we can credibly say that the products of the biorefinery are green and sustainable. The biorefinery concept that has emerged is analogous to today's petroleum refineries. However, many focus on single technologies and feedstocks such as starch, vegetables oil that could compete with food or feed. We need to create flexible, zero-waste biorefineries that can accept a variety of low-value local feedstock. Biorefineries will then be able to compete with existing industries. The main biorefinery technologies can be classified as shown here in this scheme as extraction, biochemicals, and thermochemical processes. An integrated close to zero waste system would exploit a process of extraction followed by a combination of biochemical and thermal processing that includes internal recycling of energy and waste gases, extraction of valuable chemicals prior to their destruction during biochemical and thermal treatments can significantly increase the overall financial returns. Biochemical processes have the advantage of low processing temperature and high selectivity of products generated. However, they normally require processing stage, long processing time, poor space time, and difficult downstream processing such as distillation that can be energy intensive. Alternative thermochemical routes, including gasification, pyrolysis, and direct consumption to produce oil, gas, car. These are fast but also non-specific and generally require high operation temperature, more than 500 Celsius, which reduce their energy efficiency and increase capital investment. Biochemical and thermochemical processing complement each other, and in an integrated system, they can deliver significant advantages in terms of specify of product flexibility and increasing the efficiency. Recently, green chemistry for the development of sustainable production systems require tremendous research effort of the design of catalysts through resources in efficient way. The improvement of their catalytic performance is a key goal in modern society. Several approaches using environmentally friendly chemicals and materials for less hazardous synthesis and catalysis were analyzed. The goal here is to reduce the environmental impact, especially by reducing waste, solvent, precursor, and derivatives. Here I will present some special efforts toward the use of renewable feedstock and their application, as well as the synthetic route to develop nanocatalysts using a greener chemistry. In the first figure, catalytic active palladium graphene nanocomposites was synthesized. Here is the schematic illustration of the green synthesis of the palladium graphene nanocomposite using the root extract as a bioreductant. The as-prepared nanocomposite is also applied as oxidation catalyst for the transformation of several alcohols, as we can see in this equation. The green synthesis of palladium nanoparticles for catalysis and biological applications has been also gained great interest. In the second figure, a simple and green method using LNT to reduce and stabilize palladium particles were verified, and the result indicated that the palladium nanoparticles inside the nanocomposite had a small size. In addition, the nanocomposite had higher catalytic activity toward the reduction of 4-nitrophenol than other catalysts, as we can see here in this equation. More importantly, this nanocomposite had cytotoxicity towards cell and showed a good antioxidant activity. Taken together, the prepared nanocomposites have a great potential biorelated applications. On the other hand, palladium nanoparticles have been investigated as the most effective reagent for numerous conversion reactions, such as Suzuki-Stell-Heck coupling reactions, as the catalytic performance of this nanoparticle is reliant on the shape and the size and its performance as a catalyst. In the current study here, as we can see in the first figure, a facile and an environmentally friendly technique for the preparation of palladium nanoparticles using an aqueous extract part from leaves as a bioreductant is shown here. Moreover, ionic liquid can behave as a green solvent in comparison with conventional organic solvent, but more often they also act as a ligand, co-catalyst and stabilizing agent, both for metal active species and for intermediate for catalytic system. The first figure summarizes the recent achievement in palladium catalyzed cross-coupling in ionic liquid nanoparticle for the assembly of structural, diverse, and highly functionalized organic molecules, with the focus on the cascade reaction triggered by nuclear pallidation, Suzuki coupling, Sonogashira coupling, allylic functionalization, and other type of coupling. Palladium nanoparticles obtained through previously reported facile and novel approach, as we can see in figure B. RH was grained, underwent microwave-assisted extraction, and then further purification to afford the silica product. Two types of silica material were prepared, one unrefined biosilicate and the second one pure biosilicate. Subsequently, the homogeneous palladium catalyst was incorporated onto the nanocomposite via conjugation with the amino group, as we can see in this step. These two heterogeneous final products were simply converted to the corresponding nanocomposite by a reduction step. The mechanochemical method also have emerged as a green method because they allow solvent-free synthesis of the catalyst supported on mesoporous material, especially metal oxide nanoparticles, compared with wet impregnation or co-precipitation. As proof of that, Sibera et al. Synthesized a new type of nanocomposite in figure A using a ball mill and then calcined at around 300 Celsius. This new nanomaterial was magnetically separable with a high surface area. Zeolite also has been synthesized in figure B and achieved through the solvent-free method. For instance, Zinc et al. Reported the synthesis of ZSM5 from husk ash. The mechanochemical method allowed the nanoparticle in the MOF matrix through a solid-state reaction during the sacrificial process. As a result, a palladium nanoparticle ZIF8 in the last figure, number C, using ball mill without stabilizing agent was done. The nanomaterials present a good crystalline structure with a high surface area. In addition, a mesoporous oxide was synthesized by a simple and rapid solvent-free method. Moreover, in the second figure, Pai et al. Have reported a green, innovative, and ultra-fast methodology to fabricate high-quality graphene oxide sheet by water electrolyte oxidation of graphite. The synthesis was carried out at room temperature following using electrochemical steps. Natural materials such as starch, ketosane, ketene, lignin, and cellulose have been reported also as renewable derived polymers for the preparation of active nanocatalysts as shown in the first figure. Biocompatible nanomaterials based on the immobilization of palladium second acetate on the starch hybrid system was synthesized also. Regarding this, the use of natural extract from plants to synthesize inorganic nanoparticle is a simple, economic, and efficient, and also sustainable route. The extract from leaves, seeds, roots, flowers, and fruits have been used as shown in the second figure. The extracts are composed and phytochemicals such as protein, amino acid, vitamins, polysaccharide, and organic acids. In this study, we report a new niobium zinc oxide nanocatalyst for the efficient conversion of levulinic acid, a platform molecule easily obtained from the biomass, to N-heterocyclic under mild reaction conditions and the absence of solvent. The niobium zinc oxide nanocatalysts were synthesized by a mechanochemical assisted and sacrificial template method involving orange peel valorization toward nanostructure material. Two different method approaches, either one-step or two-step, as well as the amount of niobium deposited on the zinc oxide support, were investigated in order to obtain the nanocatalyst with the optimal catalytic properties. Results revealed that the critical role of the niobium for the levulinic acid conversion. The nanocatalyst containing 10% of the niobium and prepared following a two-step approach exhibited the best catalytic activity. This work exemplifies the possibility of sustainable production of value-added compound, in particular N-heterocyclic, from biomass-derived feedstock by playing with the design of improved catalyst. Importantly, this work provides sustainable alternative to the current chemical industry that is heavily dependent on fossil fuel. Levulinic acid is an organic compound. It is classified as a keto acid with two carbonyl groups. This white crystalline solid is soluble in water and polar organic solvents. It is derived from degradation of cellulose, and it is a potential precursor to biofuels such as ethyl levulinate. The original synthesis of levulinic acid is done by heating hexoses or starch in dilute hydraulic acid or acetic acid. Moreover, levulinic acid is used as a precursor for pharmaceutical plasticizer and perfumes and a wide variety of other compounds. The preparation of the nanocatalyst involved two key points. First, exploiting the advantage of mechanochemistry as synthetic methods such as solvent-free conditions, simplicity and short reaction time, and second, the valorization of underutilized biomass residue by their use as a sacrificial template. And here we use the that is importantly favors the formation of nanostructure material with defined morphology. It is important to note that worldwide orange production represents around 52% of the total citrus fruit production, and around 60% of the orange weight is converted to peel waste in the juice industry. The two-step approach consists of synthesizing first zinc oxide nanoparticle by a mechanochemical method using orange peel and zinc acetate as precursor. The role of the biomass here was to act as a sacrificial template, allowing the assembly of the zinc acetate on the template surface via chemical and physical adherence to form transitional composite. The water from the orange peel was enough to promote the hydrolysis of the zinc acetate, resulting in zinc hydroxide, and the template also was then removed by calcination at around 500 Celsius. In the second step, here as shown in this part, the surface of the zinc oxide was modified with niobium by a simple chemical deposition procedures. On the other hand, the one-step approach was performed by mixing initially all the precursor. In both approaches, the amount of niobium loaded on the zinc oxide surface was varied and with the aim of optimizing the stoichiometric composition of the nanocatalyst. The physiochemical properties of the different nanocatalysts were determined using X-ray, diffraction, N2 physiosorption, and scanning electron microscopy, and also the XPS. The crystal structure and the arrangement of the niobium zinc oxide nanocatalyst was investigated by XRD measurement, as we can see in the first figure. XRD pattern of all sample exhibited several peaks which can be associated different crystalline plane for the zinc oxide hexagonal structure. XPS, on the other hand, of the represented sample as well as the zinc oxide as reference were carried out in order to provide information related to the chemical properties of the prepared material, and additionally to demonstrate the successful niobium incorporation of the zinc oxide nanoparticle surface. Surface area and porosity are two important physical properties of the catalytic nanomaterial due to their strong impact on the catalytic activity. Therefore, a proper characterization as well as a careful interpretation of the result is important to be able to predict which will be the optimum nanocatalyst. The non-modified nanocatalysts present a surface area, the first row, around 15 m² per gram and a pore volume around 0.1 centimeter cube per gram. The modification of zinc oxide support with niobium by using the one-step approach lead to a considerable degrees of surface area, and the pore volume values and such degrees was dependent on the amount of niobium. Indeed, for higher niobium, percentage surface area and pore volume decreased. Additionally, the effective incorporation of niobium entities onto the zinc oxide surface was further evidenced from the SIM mapping result. As can be seen, the presence of zinc oxygen and carbon was detected on all the studied sample, while niobium was only detected in the niobium zinc oxide sample as expected. The catalytic activity performance of the prepared material was evaluated in the conversion of levulinic acid toward N-heterocyclic by conventional heating in the absence of solvent. The proposed mechanism for the aforementioned reaction is shown in number A. It should be noted that the formation of the desired product was achieved through the condensation of 1,4-carbonyl compound, and in this case the levulinic acid with excess of an amine, and in particular butylamine. The reaction proceeds through a three-step, 1, 2, 3, and where the levulinic acid acts as an electrophile in the first two steps. Several studies have reported that in this case. The cyclization step, which is the second step, demonstrate and determine the rate of the reaction and involves a nucleophilic addition in a carboxyl group by the nitrogen atom of the reaction intermediate. In particular, orange peel residue were employed to control the morphology and texture properties of niobium-modified zinc oxide nanocomposite, helping to a better comprehension of the influence of sacrificial template nature and feature in the properties of the final materials. Such reactions were performed under solvent-free conditions, being also advantageous from an environmental point of view. The high utilization of biomass-derived feedstock combined with environmentally friendly procedures and heterogeneous catalyzed process could help moving on from current fossil fuel-dependent industry to a more sustainable bio-based industry. Finally, I would like to thank and express my deep thanks to Imam Abdurrahman bin Faisal University and the Dean of College of Science for giving me this opportunity to participate. And thank you all for listening.
Thank you. Thank you very much, Dr. Asma, for this presentation. If this is the time for discussion, if you have any question, just type it in the chat or the QA. box below. Meanwhile, I have a question myself. Use the orange peel. How can you prepare the solution or the powder? Do you prepare solution or the powder from the orange peel?
We dried it, calcined using high temperature, and then dry these materials, and then grind it under high temperature.
So you prepare it as a powder for your synthesis?
Yes.
Okay. Let's see if there is any question. Is there any question? Okay, thank you very much, Dr. Asma, for your speak. Thank you for being with us today. Thank you.
Thank you.
Our next speaker is Prof. Muhammad Morsi. He's a professor in the chemistry department, College of Chemicals and Materials at King Fahd of Petroleum and Minerals University in Saudi Arabia. He is a member of many scientific and professional society. Currently, he is interested in mechanistic chemistry of chemical, photo, and electrochemical oxidation using different spectroscopic techniques, mapping of oil, chemistry of asphaltenes, aging of polymer, and degradation of organic pollutions. He published more than 80 papers in journals and conferences, 1 book, and 10 patents. His speak today about crude oils, trace metal analysis by electron, paramagnetic resonance spectroscopy. So welcome, Dr. Muhammad, and thank you for being with us today.
Assalamu alaikum, everybody. I hope one of us can answer that my sound is clear or not.
Yeah, it's clear. You can
Okay.
share your screen, please.
Okay,
Yes.
good. I will. Now my screen is shared.
We can see your screen, but it's small. Can you enlarge that? Yeah,
I
please.
will. Okay. Is it clear now?
Yes, it's clear. You can start.
Perfect. I will start from the last slide. Okay, 1 second. Okay. Again, Assalamu alaikum, everyone. First of all, I would like to thank the organizer committee for their efforts, and I wish you all the best in the coming ones. We are sister universities in the same region. Today, I will going to present for you some of the work we are doing recently for the trace metal analysis using electromagnetic resonance spectroscopy. The method we are going to speak about it is our methods we produced based on some collaboration with our next door company, Aramco. And the work will going to expected to enhance the results related to the trace metal analysis. As everybody knows, the word trace means we are going to check for material within the part per billion or smaller in the quantity, and this required some technicality, and you will going to solve some challenges that could be present, and it is present due to the other, even some of the standard methods that's well known. First of all, let us speak about the Saudi Arabia crude oil. This is a space photo of the Saudi Arabia in night. These spots that you see it are actually for the oil fields that in Saudi. You can recognize most of the strong spots are at the Gulf sides, Arabian Gulf, and we are here in these zones where we can say we are on the one of the most producing area of the crude oil in the world. To confirm this is a map reflecting the main producer of the crude oil in the world, and it's very clear that the United States, Russia, and Saudi Arabia are the main producers worldwide. And because of this, mostly the people looking to the product coming from Saudi Arabia as a main source for specific type of crude oil, and these specific types can be utilized for some petrochemical industries and so on. It's well known that work for digging to find more oils and more crude oils, it's required patience and technology, as well as the quality of the crude oil is very important. This is the last decade's efforts for expanding the crude oil production in Saudi. It is clear that our expansion are in billion barrel, and this, if you notice here, related to some names like Arab Lights, Arab Super Lights, and so on. How this classified and what is the main sources of this classification is mostly takes place based on, at the beginning, on the sulfur contents and the gravity of the oil. It is very clear even by naked eye, the oils are classified with the viscosity, and the very light one, it's called light crude oils. Then some of those colored stuff until the black one moved from very light to medium light and the heavy crude oils. Everyone is employed for specific applications, and especially, as I said, petrochemical. But to have the proper classification, people all the time looking for an accurate methods to identify the components and the structures of the material or ingredients of the material included in the crude oil. It is very clear here, according to the sulfur content, that the light oils will have some percentage in weight of the sulfur, and such percentage of weight getting increased by moving to the heavy crude oil. Sulfur was a long time story, and they are looking for a way to get rid of it. To know how to get rid of it, first of all, we have to quantify. Our objective in this work, not the sulfur. There is another important material, because when we speak about weight percent, 1% or greater than 1%, this is not anymore trace metal, and it has a very clear impact on industrial plants and so on, but it is not classified as a trace metal. We look to other material, but before we go to the other material, the United States Energy Information Administration classified the Saudi oil, heavy or light, as one of those having high content of sulfur, and they are used for some application based on this classification. For the work we're going to speak about it, we will move to another species which are important when the people go to the processing the oil, especially when we move to the petrochemicals. And to do the right analysis for the work, we have to look to the map of the production of Saudi. It is very well known that one of the biggest oil fields in Saudi is the War oil fields, and into these fields and the others, there is many samples can be taken and studied due to the importances of this type of fields or well. There is a known place called the Khres, and the Khres is one of the producing fields of the crude oil. Then Uthmaniyya, Shalgam, Bqiq, Abu Safwa, Manifa, and Safaniya, and Zolfi. All of those are in blue square or blue rectangular, will be investigated in this work for the trace metals. And to do the work for the trace metals, mostly the people use the ICP, do the investigation. It's well known the ICP is reputable methods. It's producing accurate for the results for the trace metals, as it's based on the emission of the metals after converting into some specific streams that will be tested either by mass spec or spectrometry or optical spectrometer and so on. The results that I'm presenting here are listed based on the Energypedia and the collaboration with groups from R&D and Aramco. And it is very clear if we look to vanadium and nickel, these are the material are in part per million, and we will going to focus on the vanadium as a material. And from the range of the vanadium that is being reported from the ICP, it's clear that the zones of Shalgam and the Khres looks like having the same, and this helps the scientists or the industrial plants to decide are these belong to the same fields or not, based on the distribution of the trace metal, because trace metals like a fingerprint, the oil material. Now we go to the Uthmaniyya and the Bqiq and Safwan, and this looks like they have almost similar distribution of the vanadium content. Those telling that if we use the same philosophy, that these looks like very similar, but are they similar or not? We will see based on our investigation. The last one is the zone where we have Manifa, Safwa, and Safwaniya, or Zolfi and Safwaniya. And again, looks like they are from the same or have the same distribution, where the vanadium reached 50 parts per million. This was running experiments reducing this data to identify these trace metals. The trace metal has a very clear impact on the petrochemical process, especially poisoning the catalyst and so on. But it's very important to know it precisely and to look to the amount coming from each field, and also to geographically decide what are the fields that is related to each other. EBR is one of the well-known techniques as spectroscopic methods, non-destructives. It's basically two magnets with the resonators. The technology has to have detectors as any spectroscopy, but the material has to be inserted into the resonator. The material after resonating and inserted into the resonator will be irradiated with a microwave. And once it's irradiated with the microwave, if the spin of the electron for a paramagnetic species changes, we will get absorbance, and such absorbance mostly presented in the first derivative format. And This is the well-known peak for the EPR. If we have this peak, means we have paramagnetic species. Vanadium-4 is well known to be very strong paramagnetic species, and it has a characteristic peaks for their presence. And the EPR can go to nanoscale in quantity, means if we follow material in part per million, we're already at a very high range, and this high range can be detected much easier without distracting the material, and it will be precise method. For our work and other works, because we are interested in other works, we try to solve some well-known problem using spectroscopy, which are the reproducibility of the testing and positioning of the sample, orientation, by introducing one of our simply designed flow cell, where the liquids can be tested either by mixing in situ or even just flow the liquids. The sample that we are measuring can be done for even electro-oxidation process, or can be just done for direct measurements. And this is one of our recently published patent, where we prove that this flow cell was one of the successful methods to minimize most of the technical problem related to the EPR and as analytical tool. The methods can use quartz or normal glass, is compatible with most of the with all the standard resonator, means once it's been embedded into the resonator, you don't have any interference, and the results are reproducible. Also, it's easy handling material, no more orientation, because the material, the fluid under testing will go through a permanent and fixed bed for the testing resonator, and it is actually using much less quantity of the material rather than producing sample in different tubes, inserted another sample in another tube. The flow system can minimize, reduce the minimum rate possible, as well as the minimum quantity, and it can be checked several times without any contamination. This encourages us through one of the company make or to customize one of the newly distributed worldwide spectrometer. It's benchtop. The design, we call it EPR lab. This is our idea, where we have multi-modules into one spectrometer. This is new, because every time people has to reduce their modules and so on. But this module has several advantages. It can be used for photochemistry. It can be used for electrochemistry by introducing light irradiation or peristaltic pump and the potentiostat, as well as it can be used for just normal flow system. Okay, it has several advantages, and everything is now controlled by programmed, and the program very easy to reset it and reprogrammed, means it's solving one of the main problems people look for. It is the reproducibility, is the easy of the handling material, just pumping to the cells and setting the parameter. Also, we introduce Wi-Fi system to control this from any place in the lab, if not necessarily to bring the computer next to the machine. The work starts by testing three well-known oils called Arab lights and extra lights, as well as super lights. These are well defined, and they are existing in Saudi. First of all, we did ICP to check our background on all this material, as the ICP is the standard material. Then we did the PR at room temperature. Then we moved to find a best explanation of the peak that we were going to observe, and we correlate this with the vanadium oxide porphyrin, and we did the test within a range of temperature, starting from liquid nitrogen to the room temperature, and finally we tested the oils for both the trace metal and asphaltene, and we did the find the detection limit of the method we proposed. The ICP results of the sample we have, we did it for vanadium and the nickel. The results here are presenting to show how the ICP can produce the values of the three ions. It's very clear that we subdivide the material to have material as is, then we reduce the material by diluting, go to a lower concentration limits to half and to quarter using toluene solvent. And it's very clear that if you multiply by 1, the first one, and multiply by 2, the second group, and multiply by 4, the fourth group, the third group, we have to end with the same result. And it was acceptable for the 3, except the first one. It was normal that sometimes we do not have a good result from one of the trials and so on. So we do not waste our time with this result, but we said that the vanadium contents are for the super lights are within the range of 100 parts per billion and 2.8 parts per million for the extra light, and for the Arab lights is about 16 parts per million. For the nickel, we have the same. Also, we noticed some, and one of the experiments is not good. At least we know now the range that we are looking for the 3, and we go now to the EPR, and we made the test for the EPR. According to the test of the EPR, it's very clear that we have a very nice features. We have to understand this feature, and we have to correlate with what we are looking for. This is well-known feature of the vanadium 4 complexes. Okay. When we go to the extra light, we start to lose some of the feature, and the peak here it's getting less. And for the super light, we almost lose everything, and maybe a small peak here means we are speaking about clear variation in vanadium, and we have to resolve this to get trusted results. First of all, what this feature is for, it is very clear that when we have a sharp peak, the first derivative is peak, it is related to what we call it isotropic. But when we have such type of peak, one side looks like normal absorption, it's related to anisotropic. So we know that in the oil environment, the vanadium complex is slow tumbling and produce rigidly. Means we have to find if this is true or not. We produce vanadium complex with porphyrin. This is the normal spectrum for the vanadium complex. We have 8 peaks, and these 8 peaks for 1 electron interact with the nuclear spin, and such type of peaks are not similar to the one we have it from the oil, but as we said, it's related to the rigid limits, and since it's related to rigid limits, means we have to slow down the motion, molecular motion, and we do this by running the experiment at low temperature. We did the experiments from our samples from room temperature, then we start lowering to lower temperature. This is minus 140 degrees, features start showing up, minus 170 degree. This is almost the feature we have it. And then we return back, warm it up, and go back to the room temperature. But it is very clear that we have a fast sampling, and the oil is following the rigid limit that is related to the vanadium complexes. This model, which is the one that we are looking for, is now the one we will use it to justify and clarify which peaks we have to look at when we go to the analysis. The analysis was conducted by running, as showed before, for these three well-known oils, and also with the standard oil, because toluene cannot be used for vanadium. So we got standard oil with non-vanadium content, and it's very clear now by preparing variable various concentration of the oil, we can get variation in the peak, means we have the correct start. These samples from the standard oil are very similar to the samples of the true oils, and means we can use these standard systems to produce the calibration curve, and it should be precise calibration curve. We notice here that we have these foreign peaks. This peak is foreign peak, which is independent of vanadium. If you notice, all the peaks are going less by changing the vanadium content, and this peak is 100% related to variation. So we said this peak is suitable to follow for vanadium, and later we will find this peak is very also suitable, but for the asphaltene. Rather than working only for the vanadium, we also found that it's good chance to address the asphaltene content. The work is continued, and we prepare several concentrations starting from within the range that of the oil what we are going to investigate, starting from 20 parts per million to 50 parts per billion. And such type of presentation produce a beautiful linear equation using our machine. And this will be our calibration curve to test the oils in general. This is for the asphaltene, and we also able to test for a variation, low concentration of asphaltene, which was not addressed before, but we have another calibration for asphalt. Based on these two curves, we try to test oils like Arabian oil, and it's clear here that even by varying the temperature, this is at minus 100 degrees Celsius, okay, and this is at room temperature, the amount of vanadium will be sharply defined and getting better in quantity. So we said, okay, we can make two tests, one at room temperature as well as the other one at minus 100 degrees Celsius. Also, we look for what is well known in petroleum analysis to reduce the oil. And reduce the oil means we reduce the volume of the mother liquids to half and so on. And based on this, we're able to strengthen the peak that we are looking for. It's very clear that by reducing the oil, okay, it's the peak getting sharper and so on. So we can overcome some of the problem if we want. The results was for the vanadium, based on our technique, produce very beautiful results. It's telling that the vanadium in the super light is almost 70 parts per billion, about 2 for the extra light, and for the Arab light, about 40. These results are very close to what we have in the ICP, and the values we have it now are very important because based on this, we can identify several types of oils. So we went to real sample, our groups in Aramco research and developments, they provide us these samples, and we start testing this sample based on the field area using, this is a screenshot of what we have it on the computer programs, on the package, where the calibration is very clear, and once we test the material, we will get these results. Okay. The beautiful in these results, now we have another group of data based on vanadium and asphaltene results. If you notice, for the we make this table to show to you the ICP results and our EPR results. It's very clear that Sheldon and Chres, which were classified based on ICP results, are similar. Here they are not similar based on the EPR. Also, the Osmaniya, Abqiq, Abu Safa. Here we have differences, especially Abqiq. Abqiq is not belong to the same place or same distribution that the ICB produced. And the last, which is the Manifa, Zolfi, and the Safaniya, also it's produced some results where we can say Abu Safaniya and Zolfi is the same. To discuss this, we go back again to the ICB where we have this zone distribution. And it is very clear that these zones that we indicated earlier was mixing the geographics and the field exploration based on the amount was presented, and it was just mixing between onshore and offshore, and our results correct such things where the first two Osmaniya are those on the onshore, and they are almost within the Khawar field, and this is telling us that they are belonging to the same field. If we go to the Abu Safwa and Zolfi, it is different than the ICB light ellipsoid, and it's telling us we almost belong to the same field, and this is logic because of the geographic area. They are offshore and they are almost in the middle of the Arabian Gulf, and the last one, they are almost onshore, Safwaniya and Manifa, and it looks like in our EBR more accurate, and the system is more reliable than what is being presented by ICB. I can conclude that the EPR, which is working for the crude oil, can be registered at any temperature, like room temperature and the rigid limit at minus 100 degrees Celsius or so. The quantitative determination of vanadium and asphaltene was very accurate, and it produced the best methods for the vanadium content than the ICP. And it's very also clear that our ICP, our results of vanadium trace, much more accurate and gave better mapping for the oil fields, and this helped for even removing. And the work can be extended. It is already extended to detect trace metals for the petrochemical process, where we can remove the vanadium, as the vanadium mostly make several troubles to the industrial plants, especially the catalyst, where it's poisoning the catalyst. I really want to thank the team working with me, Dr. Al-Qaoud, Dr. Al-Shafi'i from Aramco, Mr. Kamran, my PhD students, and the Adani groups who actually helping us get customized machine. And this machine, as you noticed, it's very simple, easy, and they help us on the programming. Also, I would like to thank the Deanship of Research at KFUBM for funding our project. Thank you for your following this. I hope it is short presentation.
Thank you very much. Thank you for the interesting talk. Really interesting.
Thank you.
Does anybody have any question? Meanwhile, I have a question that you analyze some elements like the vanadium and the nickel. I don't understand why this specific element, the vanadium and nickel. Why did you choose these elements? Is it?
Yeah, it is excellent question. By the way, EPR is a technique only working for the paramagnetic species. it's well known the paramagnetism can be either by having radical intermediates or metals. Their oxidation state produce some of the unpaired electrons in their ionic forms, and these unpaired electrons are the reason behind the paramagnetism. For example, vanadium-4, if we make the electronic configuration as we do it for the undergraduate students, it will produce one of the unpaired electron in the d orbitals, and such unpaired electron in the vanadium-4 make vanadium-4 easily to directly followed by the EBR. If we go to vanadium-3, vanadium-2, we start to lose such paramagnetism, and means we cannot study by EBR. Again, EPR required to have paramagnetic species. Some of the paramagnetic species will also produce even a weak response because of the nuclear spin. Nuclear spin should be huge. If we can look to the NMR as the other technique similar, where we study the proton NMR and the carbon-13 NMR. Both are paramagnetic. Both are active for the NMR, but the quantity of the hydrogen, which is the proton, is high, while the quantity of carbon-13 is less, but it required some optimization. Going back, EBR is a technique for paramagnetic species, and vanadium, and when we say 4, is the only one out of vanadium series in oxidation state to be investigated by EBR.
Yeah, it makes sense now. Yeah. Thank you very much. Thank you for being here with us today. Thank you. Our next speaker is Dr. Yasser Al-Jrami. He is Associated Professor at Ohio State University, USA. He got a PhD in Radiation Protection and Dose Measurements from UTM, Malaysia. This is his 18 years in academic teaching at different worldwide university, and his 10th year at a research at radiation and medical imaging discipline. He published over 100 research articles in international peer-reviewed journals and international conferences. Yasser awarded from different national and international institutes. His talk today is about radiation shielding feature of different class compositions. Are we ready to change lead glass shielding? Welcome, Dr. Yasser. And thank you for being with us today. Dr. Yasser, we can't hear you.
Yeah, good morning.
Good morning. Good morning and welcome.
Thank you. Just I'm trying to share the right. Yeah. Just give me a second to share my presentation.
No problem. Take your time.
Okay. So good morning and thank you to each and every one of you for being here, and actually great thanks for the organizer of the second international webinar on science in Saudi Arabia. Actually, this is to say I'm proud that I have already participated in the first conference. It was in the last year, 2021. And today I'm trying to keep straight and keep on with you with this decent conference. I'm not sure if my slides is clear for you now.
Yeah, it's clear. It's clear.
Okay. So
just enlarge the
yeah,
slide, please.
Okay.
Thank you.
So I'm Yasser Al-Ajrami. I'm Associate Professor in Radiation Protection. Actually, my host university is Al-Azhar University in Gaza, and now I'm a guest researcher at Ohio State University, USA. My research interest is in the shielding materials for protection purpose against ionizing radiation, different type of ionizing radiation, medical and industrial. In this session, I will present the output of, actually, according to me, one or two of the decent researchers which gained in the last years with the collaboration of different institutes and universities. And of course, Imam Abdul Rahman bin Faisal University was one of the partners in this project. So what actually I will try to do, I'm trying to give you the output of two decent articles and projects that we have already done in the last year with the collaboration of different institutes worldwide. And I'm trying to give it under the umbrella of radiation shielding feature of different glass composition. Are we ready to change the glass shielding? So as a good thing for one of the pioneers in the medical physics, no research without action, so no action without research. This is for Carl Leuven. This is my host university at Al-Azhar University in Gaza, and this is our researcher host in Ohio State University, and this is the Edward Accelerator Laboratory that we have performed the research in it. So starting of all, just I'm trying to give a brief about what we are trying to do in our research objectives. We are dealing with a type of ionizing radiation in all or in different disciplines, in medical and in industrial discipline. We are using the ionizing radiation to give precise and good diagnosis for different patients. So as a human being, we are exposed over 90% of the genetic dose to, according to the United States population, from man-made sources. And these man-made sources, it is ionizing radiation, derives from medical exposure, and it has a genetic and mutated effect immediately and also at the long run. As you see here, the radon as one of the natural sources, it is the huge source of ionizing radiation as a human being. But now the medical source, it increased in the last 10 years and it become huge compared to the radon. What I mean here, the progress of medical dose, it's highly compared to the natural source. For that, we are trying to find a good method for shielding and using this shielding property in order to reduce the amount of radiation that reach our body. So what happens if this radiation reach our body? So we have two possibilities, direct or indirect effect. So the direct effect, it's the exposing or the direct bombarding of the DNA. And in this case, if the DNA is affected, so it means that we will get mutation, and this mutation will maybe change to cancer. We have another possibility, which is the indirect effect, which will affect on the water and cellulite of our body, the hydrolysis of water in our body. And the hydrolysis of water, it will produce two toxic substances, which is the hydrogen peroxide. And also this hydrogen peroxide, it has effect on the DNA. And this DNA also, it will be changed to mutation and cancer. So if you see here, the output is not easy. It is so difficult to understand that this type of ionizing radiation that we use to help patients, it can produce cancer. So as we say, we have direct exposing to radiation. Let's say an example, during the hospital, we're exposing our patient to different type of ionizing radiation in CT, computed tomography, fluoroscopy, conventional X-ray, interventional radiology, nuclear medicine. And in order to reduce this dose to our body as a technician or as a healthcare provider, and also to the patient, we need to follow this cardinal rule, which related to the time, shielding, and distance. We need to reduce the time as we can, to reduce the dose, we need to keep distance from the source of ionizing radiation, and we need to use proper shielding. This is our aim here. We are trying to improve the shielding. Actually, in the department, we have two types of shielding. One, it's called structural shielding for wall. As you see, the labor here or the person here, they are trying to establish structural shielding for walls to prevent the public and the outreach of this exposure to person outside the department. And we have another type, which is glass shielding. And this is what we are using in the control panel to control the patient during the exposure to ionizing radiation. So we have two types of shielding that we are trying to improve it. The structural shielding for the walls and the lead glass that we're using to control the patient during the exposure. As you see here, this is a real image from an X-ray department that show us the lead glass that we are trying to improve it. We are trying to improve this lead glass because this lead glass, it can prevent any ionizing radiation to reach to the control panel where the healthcare provider are located. And the thing that we need to understand here, that if we use a thick lead glass here, we cannot observe the patient and control the patient during the exposure. So we are trying to keep the transmittance and the transmission of visible light. At the same time, we need to prevent the absorption or the penetration of ionizing radiation. So this is the contradictory that we have and we are trying to solve. We need to keep this glass with high visible transparency. At the same time, this high visibility, it should absorb the ionizing radiation. It's not easy. And as you see here, this is the walls and the structural shielding of the entire room, the entire department, to avoid any other person or public or different section in the hospital to reach this ionizing radiation to them. So for that, to prepare this material, lead glass or structural shielding, we need to be careful about the property of this material. So actually what we need to do, we need to prepare a material with high density to be good absorber for ionizing radiation. It has high durability, which means we need a material which have high life expectancy to be cost effectiveness in order to tolerate ambient condition, at least 5 years. It's not easy to change this material every year. So at least we need durability for 5 years, cost effectiveness, eco-friendly, and easily manufacturing. And of course, good transparency for control panel shielding. So commercially standard shielding that we have it now for more than 50 years is the lead and concrete. So all the department now worldwide, they use the lead and the concrete as a shielding material. But these two materials have drawbacks. Has lead poisoning for lead. Everyone knows the poisonity of the lead. Also the environmental impact and the construction complexity when I'm talking about the concrete, and the space limitation. So these are the drawbacks that we are trying to solve. As we see here, the drawbacks that we have is the lead poisoning, the environmental impact, the construction complexity, and the space limitation. We are trying to pass and overdo these drawbacks with our new material. So this is the two articles that we have published in the decent journals and with the partnership of the American Society Journal and United Kingdom for Ceramic and Glass. The parameter that we are trying to investigate, and we have already investigated, is the physical property. When we talk about the physical property, we are talking about the density of this material. If you remember, we said that we need a high density material that has ability to absorb the ionizing radiation. For that, we need to check the physical property of the new material or the proposed material. After that, we are going to check the durability and the class stability, because we said we need a material that has life expectancy acceptable, because it's not easy to change this material every year. So we need at least to be cost effectiveness, 5 years life expectancy. And finally, we will check the shielding properties for different type of radiation, X-ray, gamma ray, neutron, alpha, and proton as well. So this is the first article, or the first parameter that we will check is the physical property. And we, of course, will check the density measurement and other related parameters. If you say we have two composition, we propose two composition to be alternative for lead and concrete. So this is our suggestion, the two composition here that we are proposed to be alternative for the lead and the concrete. The first one is the boron oxide mixed with the tellurium oxide, phosphorus oxide, and we dope it with the antimony trioxide. And the second one is tellurium oxide and silicon oxide. If you see here, we add the silicon instead of phosphorus, and everyone knows the silicon oxide and its durability. So for that, we add the silicon oxide and we get a very promising result, boron oxide and barium oxide. And here we add the barium oxide as a good absorber for ionizing radiation. The durability, when we compare the durability, when we compare the durability of the two composition, we see that the silicon oxide, the durability, it's completely different. It's significantly changed and improved. So the adding of silicon dioxide to our composition, it improved the durability and it decreased the life expectancy of glass, and it has the ability to be against any hygroscopic material for at least 6 years. And this is what we want to say, that we achieve our target of 5 years expectancy. So the adding of silicon dioxide with boron oxide, with barium oxide, plus the titanium oxide, it improved the durability and it gives us a high and promising result by life expectancy more than 6 years. Also, we started here with the shielding property, the X-ray and gamma ray, the neutron and proton and alpha. As you know, when we talk about X-ray and gamma ray, it's ionizing radiation with photon, which is electromagnetic radiation. Neutron and proton alpha are particular radiation. And exactly what we'll show in this presentation, we will show you the mass attenuation coefficient, the half-value layer, the neutron scattering, and the projectile range plus the mass stopping power. All of this type or all of these parameters are very interesting to check if this material has ability to absorb the ionizing radiation. Either it is X-ray, gamma ray, neutron, proton, or anyway, alpha. So this is the mass attenuation coefficient for the two compositions that we proposed. And if we say the mass attenuation coefficient for these two proposed at the low energy here, then we have a high mass attenuation coefficient, and it reduces by increasing of energy. So if you see here, the mass attenuation coefficient, it was high at the low energy and radically reduced by increasing the energy. And this is logic, because at high energy, at the mega voltage energy, it would be difficult to use this material, which means this material is highly recommended for the kilovoltage range. And actually, this is the range that we use in the hospital. This is a comparison between the mass attenuation coefficient of our material compared with the standard commercial one. So if you compare at the low energy, 0.2 mega electron volt, we still have low mass attenuation coefficient compared to the standard concrete and lead. But as you see, the mass attenuation coefficient here is around less than the half with the concrete in this bar and lead. But the mass attenuation coefficient of our material, it has high durability. This is the point. It has high durability. For that, maybe we need to improve the mass attenuation coefficient to be at least half or to be close to the mass attenuation coefficient of lead and concrete. And it will be our target for the coming years, inshallah. But at least we achieved a good durability. And 0.2 mass attenuation coefficient, when we reach the 0.2, the 0.2 is enough to be a good absorber for kilovoltage range. So again, if you see with me the sample 5 here, the mass attenuation coefficient, it reached 0.2 centimeter square per gram, and this percentage is enough to be a good absorber for the kilovoltage range. Of course, when we talk about the megavoltage, we need to improve this mass attenuation coefficient, and we are trying to reach the lead and shielding mass attenuation coefficient. When we talk about the half value layer here, we are talking about the thickness that we need to prepare for our material in order to absorb the ionizing radiation. What are the thickness that we need to prepare in order to absorb the ionizing radiation? So for this first composition here, at the low energy, we have low thickness, and this thickness, it's radically increased up to the high energy. So we investigated our sample at low energy and high energy, and we reached to the 15 megavolt. So we investigate our sample up to 15 megavolt. And the result showed that the half value layer is highly recommended for our sample from 10 kilovolt up to 100 kilovolt. Up to 100 kilovolt, which means in the kilovoltage range, which is the diagnostic range in the medical purpose. So of course, we can see here that the half value layer is highly recommended to be used this composition in the medical purpose in the kilovoltage range. And this material, it is highly recommended to be alternative for lead and shield at the kilovoltage range. This is the comparison between our sample here, S5, with the different standard and commercial shielding properties that located now. And as you see, the half value layer that we obtained here, what I need to say that the lowest half value layer is the best and the highly flexible material. What I mean, when you reach half value layer very small with the same target achieved, it will be cost effectiveness and it will be high manageable. So S5, our sample, it's achieved a very good thickness, and it passed around 5 types of standard commercial. And you are trying to improve this thickness to be like the SSC and the SMC, which is the steel scrap concrete and the steel magnetic concrete. So as we can reduce this thickness, which means we can use a very low thickness with a high achievable and absorbing of ionizing radiation. The same thing when we're talking here about the neutron scattering and the neutron properties. What I have explained before is for X-ray and gamma ray. When we start now with the neutron, which is the removal cross-section, we can see our achieved the sample that we have prepared from S1, S2, S3, S4, and S5, the tellurium with the barium oxide and the boron oxide, plus the silicon dioxide. We compared the removal cross-section with the water, graphite, and concrete. Of course, in case of neutron scattering, the best material that we can use to avoid reaching the neutron and to be as a barrier for neutron beam is the water, graphite, and concrete. We cannot use the lead to be absorber for neutron. Even the lead we cannot use as absorber. So we can use the water, the graphite, and the concrete. And if you say we have reached to a level which is very close to the water and graphite, and are trying to improve this removal cross-section of our material, the difference is it's around just 10% or less than 10% compared with the concrete, and around 2% compared with the water, and 5% compared with the graphite, which means we are very close, and we are doing our best to improve this removal cross-section to be used for neutron purpose shielding. لما نحكي عن neutron هنا, when we talk about the neutron, we are talking about the industrial purpose, not the medical purpose. And this is the neutron scattering for different properties. If you see with me here, starting from A, this is the, this is the coherent neutron scattering. And if you see, by increasing the concentration of barium oxide, every time we increase the percentage of barium oxide, the neutron scattering length, it will reduce in A, B, and C. And when we increase the barium oxide, for the incoherent neutron scattering, it will be increased, and this is highly recommended to be used for the neutron scattering. So according to the neutron rules regulation, if you have scattering of a neutron that it reduces by increasing your material for the coherent and scattering length and scattering cross-section, plus increasing of this material with the incoherent scattering and absorption neutron scattering, this means that your material is highly a dopant for the neutron shielding. So now we move to the proton and alpha. And proton and alpha we can use in both, in medical and industrial purpose. For proton and alpha, we check two types of parameter, which are the most significant types of parameter. The first one is the mass stopping power. And if you see the mass stopping power, it increased by increasing the energy for all samples, and the peaks, it was at around 1 megavolt. Above the 1 megavolt, it reduced, which means that we can use our material for shielding for low energy and up to 1 megavolt. Talk about the proton, and the same or very close with alpha we have achieved for this material. Even when نتكلم عن proton and alpha, when we talk about proton and alpha and the usability of our material to be shielding for proton and alpha beam, we can use our material to be a good shielding for proton and alpha, starting with the low energy and up to 1 megavolt. And this is a very promising result in the medical and also industrial, that we can protect the healthcare provider and the industrial workers from the high megavoltage of proton and alpha up to 1 megavolt by using this high durability material with silicon dioxide and tellurium. So this is just, at the end, I want to show you the experimental setup that we used at the Edward Accelerator at the Ohio State University. So this is the sodium iodide with thallium that we use as an ionizing radiation detector. This is our material, the yellow glass here, and this is the shielding that we used, and this is the radiation source that we used to calculate the mass attenuation coefficient and the half value layer and the different shielding property. So this is our setting up according to the Lambert-Beer law, that we use it to expose our material, and this it occurred at Edward reactor irradiation at Ohio State. And also, we compared our result with the theoretical and the experimental one with a simulation that we performed at Imam Abdul Rahman bin Faisal University, the Monte Carlo, version 5. So one of the pioneer researcher at the Imam Abdul Rahman bin Faisal, his name is Muhammad Muharib. He performed this simulation and it gave us a very close result to the experiment. It gave us a very good result, which is very close to the experimental one. And this simulation, it gives us the opportunity to improve and to continue our research based to this simulation instead to recurrent or to use a highly cost material. So this is a good simulation now, and the code now we have it to be used in order to improve our result in the future. The theoretical one, it's already published in the XCOM program available online, and anyone can get it through the XCOM program, which is a soft and friendly. It's available free, and you can check the result by using this theoretical XCOM program. The conclusion: we have get a high radiation shielding property, which are achieved with the proposed glass system. The borate glass is highly recommended to be used as a shielding barrier alternative for the lead and concrete. The barium oxide, the phosphorus oxide, and the tellurate plus the silicon dioxide showing a very promising result and improve the shielding property, especially for X-ray and gamma ray at the low energy, at the kilovoltage energy. Above all, we still need to investigate the ability to complete and release and substitute the lead glass with our new composition. Just I want to say thank you for all my colleagues and my partners at this project from Ohio State, from Imam bin Faisal, from Israel University. So just I want to say thank you, and also thank you for your attendance and to be with us today. Thank you very much, and you are welcome for any question.
Impressive. Thank you very much for this amazing talk. I have a question myself. We know that one important parameter is the durability of the material, right? How can you measure the durability and the glass stability? I can see that you measure it 23 days or 40 days, something like that. How can you make sure that or estimate that it's good for 5 years, for example?
Okay, this is a very good question. Actually, we check the durability for 1 month as a maximum, but we have a simulation that we can take the parameter from the 30 days or from 1 month, and based to this simulation, we can expect the durability of or the highest durability, the highest life expectancy of your material. So our experiment performed for 30 days, as a maximum for 40 days. In some cases, we can do it for 2 months, but we have another simulation that we can take the parameter from this simulation to get the expectancy of 5 or for long years, up to 10 years. So we have a simulation that you can use it to take the experimental durability and to get the highest life expectancy of your material.
Okay, right. Okay. I have another question, then we'll move to another question from the audience. But another question which is related to, I know there are a few parameters you have to meet, especially the transparency you have to achieve, not only the shielding itself. So I can see that you use the oxides material. Is there a reason for that? You can use, for example, a sulfides material like antimony sulfide or any material that's different from the oxides.
Okay, this is a very good question, but you know, we have a contradictory here. What I mean here, we are trying to get high durability, high transparency, and at the same time, we are looking for a high density material. We are looking for a high absorber material that has the ability to absorb the ionizing radiation. In order to that, we need to make a mixture between the oxide, different oxide, with some material that has the ability to get the brightness, to get the transparency, and at the same time, we need to keep the transparency as we can do that, because we need the transparency for monitoring our patient. For that, we can see that we have different material in our composition. At least we need to add 4 to 5, sometimes 6 element in our, or 6 oxide in our composition, in order to get the balance between the absorbing of ionizing radiation and to keep straight for the controlling and the transmittance of visible light.
Okay, thank you. We have Dr. Muhammad need to share the discussion.
Yeah.
Assalamu alaikum. Assalamu alaikum. How are you, Dr. Yasser?
Hi, Muhammad. Hi.
My
Good,
colleague,
I'm
Dr. Yasser,
happy
in the
that because
BSG.
you are here.
Thank you. Thank you, Doctor. Dr. Yasser, as my colleague in the, during the PhD trip in the University of Technology, Malaysia, mashallah, a very good presentation, and you talk in everything and shielding, and give a good example for shielding parameter and everything, mashallah. I don't have any question because you know, in this area I know everything, inshallah, almost, not everything, but alhamdulillah. But Doctor, my question now, will you expect get a sample better than the lead or lead glass material? Do you expect?
So actually, thank you for Dr. Muhammad. Actually, he's one of the very active researchers that I'm happy and I'm proud to work with him. And
Thank you. Thank you.
as you say, these are very tricky questions. And to be honest, it's not easy. It's not easy. And up to this point, we hope or wish that we can get a material to be alternative for lead. But up to this point, if you say we are trying to solve a problem, we can face another problem. So we solved many of problems like the durability and the poisoning and the toxicity of the lead, but we still, when we talk the high absorption of lead and concrete, we still face challenges to do that. So according to my experience or my little bit experience, we cannot do that, at least for the 10 or 20 years. It's difficult to do that.
Okay, Doctor. Dr. Tahani, do you ask about? Did you ask about maybe material, not oxide material? I think there is a lot of material like alloys and chalcogenetic glass. Maybe you can use in this area.
Yeah.
Okay, great.
Great. But you know, we should have a material with low cost, because this is one of the
the cost effectiveness.
Effectiveness, should be choose material with low costs for this purpose.
Right.
I would like to thank Dr. Yasser for nice presentation.
Thank you, Dr. Muhammad. And thank you for all of you. I'm really proud to be a participant with you for the second year.
Thank you, Doctor.
Thank you very much. It was an amazing talk, really. Thank you for being with us today. Thank you. Our next speaker is Dr. Asala Zahrani. She's Associated Professor in Chemistry Department, College of Science at Imam Abdul Rahman bin Faisal. She's received her PhD in Physical Chemistry from University of Petra, Malaysia in 2020. Her research focuses on synthesis and characterization nanomaterial thin films for photoelectrochemical application. Also, Asala is the author for more than 15 published papers in Index Journal. She awarded the RSC Congress Poster Award at the 11th International Fundamental Science Congress. And also she has been awarded the Best Oral Poster in the sixth International Conference on Nanotechnology, Nanomaterial, and Thin Film for Energy Application in 2019. Her talk today is about the enhanced photoelectrochemical performance of the bismuth sulfide, sulfur sulfide, zinc oxide, novel ternary heterostructure. So welcome, Dr. Asala, and thank you for being with us today.
Thank you very much, Dr. Tahandi. Just give me a few seconds to share my screen, please.
Okay, go ahead, no problem.
Is it clear now?
Yeah, we can see your screen, yes.
Okay, thank you very much. Assalamu alaikum wa rahmatullahi wa barakatuh. Alhamdulillah, wa salatu wa salam ala rasulillah. First of all, I would like to thank the International Webinar of Science's Sustainable Development and the Ecosystem in Saudi Arabia for giving me this opportunity to present my work entitled Enhanced Photoelectrochemical Performance of the Bismuth Sulfide, Sulfur Sulfide, Zinc Oxide, Novel Ternary Heterostructure Nanorods. My outline presentation today includes background of a study, objective of a study, methodology, result, and discussion, and I will close my talking by the conclusion. With the development of the industry, the traditional energy sources are largely consumed, and the environmental pollution dramatically harms people's health. So, seeking for alternative sources of energy becomes a crucial step to avoid many crises in our environment and our health as well. So the alternative sources energy should be affordable, workable, and eco-friendly. Among the alternative sources energy, solar energy is an ideal choice because of its limited and eco-friendly features. Basically, there are many technologies can be used to convert the solar energy. The photoelectrochemical cell is regarded as one of the most favorite conversion protocols for effective conversion of solar energy to the chemical, then to the electrical energy. As you have seen here in this schematic, this is the BEC cell, and we can see here that we have 3 electrodes. One of them is the working electrode. That's why, to ensure the best performance of the photoelectrochemical cell, more attention should be paid to the synthesis of the working electrode material. In the recent decades, one-dimensional semiconductor forms of the nanorods, nanowire, nanopulse, and nanotubes were used broadly in the electronic and optoelectronic applications. Among the IDs, zinc oxide has an excellent electronic and optical properties, such as wide band gap energy, 60 milli-electron volt, exciton binding energy, and electron mobility. However, the wide band gap energy of the zinc oxide nanoparticles just only a small portion of the visible light. Therefore, we need to enhance the ability of the zinc oxide nanorod of harvesting the visible light. Among of the technique strategies that can be used in this regard is using the sensitization of the surface of the zinc oxide nanorods using narrow band gap energy of metal chalcogenide. But again, we have another problem need to overcome in this regard, which is high recombination rate, which is considered one of the most popular problem with using narrow band gap energy, such as bismuth sulfide and sulfur sulfide. So the strategy that can be used to overcome this problem, use the strategy of a nanocomposite material, I mean metal chalcogenide over the metal oxide-based semiconductor nanofilm. We can adopt it because it's become crucial in the solar conversion technologies because of their great efficiency, flexibility, and stability. By looking into the literature review in our scope of research, we can see that the bismuth sulfide and sulfur sulfide, zinc oxide, have been successfully made, but only limited reports have been done on the bismuth sulfide toward the BEC application. And the obtained photocurrent response, as you have seen here, and the photoconversion efficiency need to improve. And I think it's worth it to mention that no report has been published in the deposition of the bismuth sulfide, sulfur sulfide, zinc oxide using successive ionic layer adsorption and reaction, So the novelty of the important contribution in the improving band gap structure cascading of the ternary composite by simple and low-cost method in order to adding to the existing knowledge. The aim of this study is synthesize a cascade structure of the ternary nanostructure, bismuth sulfide, silver sulfide, zinc oxide nanorods in indium tin oxide using two strategies or two methods, starting with eco-friendly hydrothermal method, then specific ionized layer adsorption and reaction cellular techniques. Then study the effect of the annealing temperature in the photoelectrochemical performance of the ternary heterostructure. Then compare the photoelectrochemical performance with the plane and binary heterostructure. Starting with the methodology, actually we achieve our goal to prepare the ternary heterostructure. We started with the prepare zinc oxide nanoparticles, the seed layer. And in this regard, we use the sol-gel spin coating method. And the precursor solution for the coating consists of zinc hydrate, hexahydrate, and also diethanol amine. And these precursor stirring at 60 degrees centigrade for 30 minutes, then aging at room temperature for 24 hours to obtain more colloid solution. Then after that, around 100 microliter of the precursor solution subjected to the spin coating, and the 3 cycles has been repeated to obtain 3 workable layers. The result from this step subjected to the annealing at 350 degrees centigrade for 1 hour with the heating rate of 2 degrees per minute. The result from this step, actually, after that, use it as a substrate to prepare the zinc oxide nanorod with using the growth solution. Actually, the novelty of our method here that we will not use, we didn't use the autoclave. Instead of that, we use a glass pills type. So the zinc oxide nanoparticles from this step upturned in the glass pills and filled with the growth precursor consists of zinc nitrate and hexamethanol tetraamine with the ratio equals to 1:1. Then after that, the glass pills loaded in a preheated of silicone oil, bath for 4 hours at 110 degrees centigrade. Then after that, the result keep to cool down at room temperature and rinsing with the deionized water many times. Then after that, keep in a dry condition for further fabrication. Then after that, to achieve our goal to prepare ternary heterostructure, we should start to prepare binary heterostructure consists of sulfur sulfide over the zinc oxide. So the obtained result from the previous step, this one here, zinc oxide nanorods, used as a substrate in the cellular method. Actually, in cellular method, we have 4 different steps, starting with the adsorption. So the zinc oxide nanorod as a substrate dipped in the precursor solution consists of the cationic precursor consists of AgNO3 for 1 minute. Then after that, dipped in deionized water to remove any lossy bond. Then after that, the reaction starts with Na2S for also 1 minute. Then after that, with the deionized water to remove any lossy bond. As you have seen here, these 4 steps are considered 1 cycle. So we repeat these steps 7 cycles to get 7 cycles of bismuth sulfide, sulfur sulfide over the zinc oxide nanorod. Then after that, the result from this step annealed in the nitrogen gas at 400 degrees centigrade to obtain binary heterostructure comprised of Ag2S zinc oxide nanorod. The same technique used again to prepare the last layer of bismuth sulfide over the Ag2S, and this time we use the precursor consists of bismuth nitrate and also Na2S as a cationic and anionic precursor respectively, and the time in this time was 15 seconds. Then after that, the result from this step repeated 6 times to get a 6 cycle thin film. Then after that, the thin film from this step subjected to the annealing at different temperature ranging between 100 degrees centigrade to 500 degrees centigrade to study the effect of the annealing temperature in the performance of the ternary heterostructure. So for the results and discussion, as I mentioned before, the aim of this study to study the effect of the annealing temperature on the performance in the BEC. But before that, we're going to see what the differences between the plane, binary, and the ternary heterostructure. So the result and the discussion will follow this order. We're going to all the time to make a comparison between the plane, binary, and the ternary heterostructure, then look for the effect of the annealing temperature. And as you have seen here, this is the system result of the plain zinc oxide binary heterostructure and the ternary heterostructure, and it can be noticed that the zinc oxide nanorod were well aligned in vertical orientation with the new uniformly growth, as you have seen here in the cross-sectional. So the diameter of the zinc oxide nanorod equals to 37 nanometer with the aspect ratio of around 20.45. So the vertical growth of the zinc oxide were expected to provide us a large surface area for the deposition of the bismuth sulfide and sulfur sulfide, and that's what we are looking for in BEC application. After the deposition of the bismuth sulfide, we can see here that the decoration of the small nanoparticles of the bismuth sulfide and sulfur sulfide cover the surface of the zinc oxide without alerting the zinc oxide hexagonal vorticite structure. And apart from the effect of the ternary heterostructure, we can see the surface of the zinc oxide becomes closer after deposition the two metal sulfides over the zinc oxide as a ternary heterostructure. And we can see here that the particle size, you can see here the effect of the annealing temperature on the morphology structure of the zinc of the ternary heterostructure at different annealing temperature. Apart from the effect of annealing temperature, we can see that the particle size increase by increasing the annealing temperature, and this can be due to the centering of the small nanoparticles during the annealing process. The elevate the heat temperature higher than 400 degrees centigrade, we can found here that there is extraordinary expansion of the nanoparticles over the zinc oxide nanorod in a way that can clog the gaps between the zinc oxide nanorod and affect late the penetration of the light and also the solvent, as I will explain later in the BEC performance, inshallah. As you have seen here, the particle size, as I mentioned before, increased by increasing the annealing temperature as a result of the centering of the small nanoparticles. For the check the crystallinity and the purity of the obtained thin film, we have already done the XRD for the zinc oxide plane nanorod, and also before and after the post-heat treatment. And we can see here that the zinc oxide has hexagonal vorticite structure with the well orientation along 002 plane, and also the Ag2S has a monoclinic structure, while the bismuth sulfide has orthorhombic structure, and both of these or three of these phases occurred obviously in the ternary heterostructure. Apart from the effect of the annealing temperature on the XRD pattern, we can see that some diffraction peaks, as you have seen here, some diffraction peaks increase in the term of their intensity with increasing their temperature, but started after that to decline after 400 degrees centigrade as a result for the expansion, which that means poor crystallinity of the ternary heterostructure at this particular temperature. The absorbance or the optical properties is very important in the BEC application. That's why we're going to conduct some UV spectra for all the obtained thin film. And as you have seen here, the absorption spectra of the zinc oxide before the sensitization, the surface of the zinc oxide show the absorption age less than 400 degrees centigrade as a result of its wide band gap energy equals to almost 3.22 in this study. After the deposition, the bismuth sulfide, sulfur sulfide as a ternary heterostructure, we can see that there is a good improvement in the optical properties, since the absorption age of the heterostructure now has a rich shift for long wavelength, and we reached almost 800 by the optimal condition, which is 400 degrees centigrade. We utilize from the absorbance spectra to study or to calculate the band gap energy using a Tox plot, and the results show that there is a systemic reduction in the band gap energy from 3.22 to 1.56 electron volt, and this is as a result of the good crystallinity that can help with the good penetration for the photon, which can help us to improve the optical properties of our material. So for the BEC performance, the bismuth sulfide, sulfur sulfide annealed at a different temperature were applied in a BEC system, similar to that I have already displayed in the second slide for today. So to assess the performance of our obtained thin film, we assess that in the condition of dark and illumination using solar spectrum simulation, solar spectrum using the halogen lamp with the power intensity equals to 100 microwatt per meter watt per centimeter square. And we can see here from these results, you can see that there is a good enhancement in the photocurrent response or current density by deposition, the binary heterostructure, and also ternary heterostructure. Comparing with the before and after treatment or post-heat treatment, we can see that there is increment in the photocurrent density by increasing the temperature from 100 to almost 400 degrees centigrade, and we achieve the highest photocurrent density equals to 12.95 milliampere per centimeter square before showing the decrement at higher temperature 500 degrees centigrade. And it can be suggested that these improvements in the film crystallinity with improved the absorbance property and minimizing the recombination center could induce the better separation of the electron hole, leading to the increase in photocurrent produced, as we mentioned before, in the regard of the optical properties and the morphological structure. Moreover, the post-heat treatment, as we know, can decrease the defect within the thin film as a result of decreasing the number of grain boundaries within the ternary heterostructure. All these factors can attribute to these enhancements that happen in the BEC performance. We utilize the results or data from the BEC or linear sweep voltammetry to calculate the photoconversion efficiency. And as you listed here in this table, we can see the photoconversion efficiency increased dramatically by increasing the annealing temperature from 100 to 400 degrees centigrade before showing the decrement at 500 degrees centigrade because the expansion of the nanoparticles that clog or block the gaps between the zinc oxide nanorod and limit the penetration of the light and also the electrolyte during the BEC process. So, for explanation for the dynamic, for the electrochemical and BEC process occurring to the photoelectrode, the EIS analysis has been done. And as you have seen here from this chart, we can see that the meter of the semiconductor of the bismuth sulfide, sulfur sulfide photoelectrode is smaller comparing it to the plain zinc oxide nanorod and also the binary heterostructure, and also comparing it to the deposit material as a ternary before treatment. So we can see that the transfer charge or the charge transfer resistance decreased from 12,000 to around 3,587 ohm per centimeter square, which means that the resistance of the thermally treated bismuth sulfide photoelectrode is smaller. That can greatly and effectively improve the separation of the photo-generated electron hole pairs. Apart from the examine our ternary heterostructure, actually we have already done a high resolution transition electron microscopy, and we can see here from these images The TM shows the smooth surface of the zinc oxide before the deposition. After the depositor Ag2S over the zinc oxide, we can see that small nanoparticles start to distribute over the zinc oxide nanorod without affecting the hexagonal vorticized structure of the zinc oxide. The diameter of the Ag2S distributed here equals to 10.88 nanometer, and after the deposit, the visible sulfide over the Ag2S zinc oxide, we can see the surface of the zinc oxide became closer than before, since the nanoparticles distributed with diameters equals to 20.88 nanometer. Apart from this, we can see here that from the HRTM, we can see that we have 3 lattice fringes. Spots belongs to the zinc oxide, bismuth sulfide, and silver sulfide. By applying the fast Fourier transformation, we can see that or proof the polycrystalline nature of the ternary heterostructure, since we can see the polyspots here, which confirm the polycrystalline nature of the obtained ternary heterostructure, with the D spacing equals to 0.23, 0.31, and 0.26 nanometer, which corresponding to the bismuth sulfide, silver sulfide, and zinc oxide, respectively. Also, we have already also done EDS pattern and element mapping, EELS, for the ternary heterostructure to prove the purity for our obtained thin film. And from this result, we can see that only the element zinc, oxygen, sulfur, bismuth, sulfur, and sulfide and indium has been detected within the ternary heterostructure, and the indium actually attributed to using the ITO substrate. For this reason, indium comes from that. For study the electronic structure and more information about the binding and quantitative study, binding energy and also oxidation state to prove the existence of the bismuth sulfide and also silver sulfide over the zinc oxide with the strategy of nanocomposite, we have already done or conduct our sample in the XBS analysis. So from the XBS analysis, XBS survey, we can see that just only the bismuth, zinc, oxygen, and the sulfide has been detected within the our thin film. And by running the XBS for high resolution and narrow, we can see that all the binding energy that's calculated from these results is in a good agreement with other published paper, which means ultimately the coexistence of the sulfur sulfide, bismuth sulfide, and zinc oxide within our prepared sample. So in order to see what the reason behind these enhancement that we saw during the process of BEC, we can say that the heterojunction architecture allows more incoming light and increase the separation of the charge for the photo-generated electron. And as you have seen here, the electrons from the electron in the bismuth sulfide, silver sulfide, zinc oxide, once they excited from the valence band to the conduction band, so after that, the bismuth sulfide electrons can transfer easily from bismuth sulfide to the silver sulfide, then after that to the zinc oxide easily, and existence of the Ag2S as a intermediate layer act as a highway path for the electron to transfer easily from the bismuth sulfide with the more negative potential energy than the Ag2S than the zinc oxide. And this way of cascading band alignment of the energy can help us to reduce the recombination process that can all the time affect the BEC performance. At the same time, the accumulated holes in the zinc oxide transfer easily to the silver sulfide, then to the bismuth sulfide. By the end of this presentation, I want to conclude what I have already talking about today. So the effect of the heat treatment was pronounced as the performance of the ternary photoanode was 2 times better than without the heat treatment, and also the ternary tear structure nanocomposite annealed at 400 degrees centigrade showed a obvious enhancement in the photocurrent density with almost 12.90 8 milliampere per centimeter square, which actually around 38 times greater than compared with the plain zinc oxide nanorod. And also we can see that the photoconversion efficiency enhanced about 50 times higher than that of the plain zinc oxide nanorod. And this impressive of the enhancement can be attributed, as I mentioned, to the ternary electrode that exhibit enhanced visible light absorption, which could increase the amount of the photo-generated electron produced. So the next step now, we are conducted some experiment to see the effect of adding one more layer to get the 4 layers above the zinc oxide nanorod to see is there an enhancement in the ability and how this can play a significant role to create a new pathway for the photo-generated electron for more enhancement in the BEC performance. By the end of this presentation, I would like to thank all you. And if you have any questions, ready for any questions.
Thank you very much. Thank you.
Thank you. Thank you very much.
Thank you for your great presentation. Let's see if anybody have any question. Just wondering, you measured the efficiency. It was about 12%, right? The highest one at 400 degrees, right? If we compare this efficiency to material that already published, for example, for bismuth sulfide alone or bismuth sulfide with zinc oxide, for example, because there is no published paper on the 3 structure, which is the heat structure.
Yes.
Is it comparable or the result, I mean, the efficiency? Because at the first you show us a table that it has the published work.
Yes, this is excellent questions, and I want to highlight something. Actually, when we are talking about the BEC performance, or actually about the photoconversion efficiency, we should keep in our mind that many factors that can affect the final result for the photoconversion efficiency. For example, the morphology, as I mentioned, also the optical property, and also some complicated electrochemical process that happened. So selecting the best material is important, but we should keep in our mind that the overlapping with our factor that can affect photoconversion efficiency. So when we can make a comparison between our results that we obtained from this study and other results similar to our system, we can see that actually these results has been done after many attempts to optimize all the conditions that can help us to achieve this goal. So the good optimization for the result or for the condition can help us to enhance the photo-induced charge carrier and also limit or reduce the recombination process. So when we make a comparison, we should study all the factors that can affect it. Then after that, we can make a reasonable comparison between one. Since we can, some people can did the same thing, but using a different technique, using a different conditions, so they can get different results.
Yeah, right. Thank you very much. Thank you again for your participation. Thank you. Our next speaker is Dr. Aruna Shlam. He is Associated Professor and Head Department in Chemistry, Electrochemistry, Savitha School of Engineering, Savitha Institute of Medical and Technical Science in India. He designs, develops, and ruthenium Schiff-based complex nanocomposite for catalyzing the organic reaction and also to decompose the organic pollutions by photocatalysts. He is a life member in various journal and chemistry associations. He also serving as an editor board member in the reputed journal. He is also published more than 45 articles in the international journals. He is also peer-reviewed in various journals. His title for his speech today is Synthesis and Spectral Analysis of some ruthenium Schiff-based complexes and their application and unusual behavior of copper. Welcome, Doctor. And thank you for being here with us.
Thank you for your thank you, ma'am.
Thank you. You may share your screen, please.
Great process. Yes, ma'am. Ma'am, the screen is visible, ma'am. Professor, the screen is visible.
Yes, we can see your screen.
Thank you. So I'm happy to be with you all in the wonderful session. So I'm going to present my title as Synthesis and Spectral Analysis of some ruthenium Schiff-based complexes and their applications and the unusual behavior of some copper complexes. Okay. So while comparing with the eminent speaker's presentation, I'm going to present the traditional work. Okay, so you are all doing the advanced research, and apart from that, I'm going to have the presentation by having the traditional one, more specifically from inorganic chemistry. Okay. So let us start from the Hugo Schiff. So he is the first concern who born in Germany, and he is the concern who reacted the aldehyde and ketones, which is having the C double bond O group with the primary amines, that is R single bond NH2, and he forms the aldimines and ketimines. And in another case, we can call the compounds as the Schiff bases. Okay, so that is the characteristic reactions for the organic chemistry for the conformation of organic compounds. Okay. So here we have the definition. So the Schiff bases were derived by the reaction between the aldehydes as well as the ketones with the primary amines, and here we have the elimination of double bond O present in the carbonyl group of the aldehyde or ketone, which leads to the formation of a C double bond N. Okay, so this is the small introduction about the Schiff bases, and we have the characteristic reactions for the synthesis of Schiff bases. Here you can see we have the primary, R single bond N, and we have the ketone or aldehyde, maybe alpha aromatic. So you can see have the condensation between the hydrogen of primary amine and oxygen of a carbonyl compound, which leads to the formation of aldimines or ketimines. Okay, so whenever we have the presence of C double bond N, and then we can consider that as a Schiff base. So here we have the another example. There is a methylamine with the acetaldehyde, which leads to the formation of an aldimine. And in next case, we have the condensation of a NH2 group with the ketone. Here we have the ketimines. Okay. So if we derive the Schiff base C double bond N compound by the reaction between prime and if we have the same by using the ketone, then we can call it as ketimines. Okay. So we are going to use these Schiff base compounds as a ligand, which is going to get coordinated with the metal complexes. Okay. Whenever we have the formation of a complex by having the Schiff bases, which increases the reactivity of the metal complexes. Okay, so here I have selected the ruthenium complex. Okay, so before going to that, we all know that naturally occurring metal complexes, all the metal complexes existing in the environment is a major metal hemoglobin, the iron, Fe2+, whenever we have the oxidation and reduction of iron takes place in hemoglobin, that leads to the oxygen transfer. So the hemoglobin behaves as an oxygen carrier in the blood, and at the same time we can have the chlorophyll. We have so deviations in the substitutions when compared to the hemoglobin and the chlorophyll porphyrin compounds. And here we have the availability of magnesium 2+ ions in the central core. So we have we call that as the chlorophyll, which is more responsible for the photosynthetic process. And among the noble metals, I have selected the ruthenium. Okay, so ruthenium is a very good property, chemically active. So by incorporating ruthenium, starting with the Schiff-based complexes, we can have the variety of applications, maybe in the industrial applications, as well as in the medicinal applications. So we can go for designing the drugs which can be used as the anti-cancer or antimicrobial medicines. And in the case of industrial applications, we can go for the carbon-carbon coupling reactions or oxidation of alcohols. Variety of organic reactions can be catalyzed. So by in my presentation, I have selected the 2 ruthenium metals starting trichlorotris triphenyl phosphine ruthenium, and in another case tribromotris triphenyl phosphine ruthenium 3. So here the oxidation state of the ruthenium is +3, and I have selected 6 ligands, and I have characterized the synthesized complexes as well as the ligands by using the elemental analysis, FTIR spectroscopy technique, electronic spectra, proton NMR spectra, EPR spectra, and then the cyclic voltammetry. And we have the applications. So we have the oxidation of alcohols, aryl-aryl coupling reaction, and then the last one is the biocidal activity. Okay. So we have the synthetic procedure for the synthesis of ruthenium metal starting. So we have to take a millimolar solution of ruthenium trichloride along with the triphenyl phosphine in the presence of HCl. We have to reflux all the reactants in the ethanol for 1 hour, and we get the reddish brown crystals of ruthenium trichloride plus triphenyl phosphine. And in the case of RuBr3 ppH3 thrice, we have to go for the addition of RuCl3 triphenyl phosphine, lithium bromide, and HBr in the, it has to be refluxed in the ethanolic medium for 1 hour, and we get the green color crystals of RuBr3 triphenyl phosphine, triphenyl phosphine, and we have the synthetic procedure for the ligands. So here you can see we have the diketone. Okay, so this diketone should be reacted with the substituted compound, maybe the aminophenol, aminothiophenol, and the anthranilic acid, aminophenol carboxylic acid, aminophenol phenyl carboxylic acid. So here you can see, here we are having the NH2 group, so the primary amine. So the 2 hydrogen from this primary amine will get reacted with this oxygen, and we have the formation of C double bond N. So this is, so here we have one condensation product, and the same type of condensation can be done in the another carbonyl compound. Okay, so whenever we increase the reaction time more than 3 hours, the ketoenol tautomerism gets removed, and finally we have the formation of this Schiff-based compound. Totally we have the 6 Schiff-based compounds. So in the first one we have the hydrogen substitutions in the phenyl group. So here we have the phenolic OH functional group, and in the second one we have the thiophenolic functional group, and in the third one we have the carboxylic acid functional group, and in the second category of ligands we have the methyl group substrated in the phenyl ring of the diketone, and the remaining were same. And this is the synthetic procedure for the preparation of the ruthenium based complexes. So we have to reflects the equimolar solution of the ruthenium metal starting along with the shift base ligands in the benzene medium. Okay, so here you can see we have the nitrogen. So this imine group is neutral site. So therefore it eliminates one triphenyl phosphine from the ruthenium starting, and this one again eliminates the another triphenyl phosphine, and we have the availability of a single triphenyl phosphine group in the ruthenium metal starting, and this YH, maybe the OH or SH or COOH. So this proton gets deprotonated, and then this deprotonated proton will combine with the halides, maybe the Cl minus or Br minus, and we have the formation of byproduct HBr and HCl, and then we have the formation of an ionic bond between the Y and ruthenium. That is the O or O minus or S minus or COO minus, and finally we get the product like this. Finally we can get the shift base complexes. Okay, so this shift base complexes formed can be easily separated from the benzene medium by adding the petroleum ether. So that can be precipitated by adding the petroleum ether, and then I tried a number of times for the development of crystals. So I tried a lot and I failed in the development of crystals, and then initially I characterized the shift base ligands and the metal complex, the ruthenium metal complex, by having the FTIR spectra. So here you can see we have the availability of different ranges. So by considering the presence as well as the absence of the functional group, we can consider the formation of bond between the different functional groups. So here we have, you can see we have the tentative representative spectra, and we have the tabulated values, spectral data. So here I have mentioned the FTIR spectra as well as the electronic spectroscopy values. So by having the FTIR spectra, you can see the variations in the C double bond N group characteristic frequency value. So in the free shift base ligands, we have the bands in the range of 1603 to 1667 centimeter inverse. So this is the characteristic frequency which can be expected for the azomethane group, that is a C double bond N group, and the same can be shifted towards a lower frequency in the case of the complex, because the lone pair of electrons available over the nitrogen is donated towards the central metal atom, and therefore the value gets decreased. So therefore you can see we have the decrease in the value. So here it is 1600 to 1667 range, and here you can see we have the decrease in the value 1538 to 1657 centimeter inverse. Okay, so that decrease confirms the formation of bond between the azomethane nitrogen to the central metal atom. And this next one we have the phenolic OH. So here in the case of the phenolic OH, we have a strong band which was observed in the range 1310 to 1330 centimeter inverse. So which confirms the presence of the availability of a phenolic CO stretching, and same time in the same phenolic CO group in the complex, this shifts to the higher region. So it shifts to the higher region from 1300 to 1400. Okay, because from the phenolic OH, the O atom donates the electron to the ruthenium. Okay, we know that oxygen is more electronegative in nature, so the sharing of electron from the highly electronegative atom increases their frequency in the case of FTIR spectroscopy. Okay, and also we have the disappearance of the peak for the OH moiety. So the phenolic OH moiety will get disappeared in the respective complexes. So that confirms the deprotonation process. So the deprotonation process is the route for having the formation of bonding between the phenolic O to the ruthenium. Okay. So therefore, the disappearance of the broad band for the phenolic OH confirms the formation of a bond between the phenolic O with the ruthenium. And then we have the thiophenolic SH functional group. So here in the case of the thiophenolic SH group, here we can expect the peak around 260 centimeter, and after the formation of a complex by having the deprotonation, you can see we have the decrease in the peak value. So when compared to the oxygen, the electron negativity of sulfur is less. So therefore, here we can have the So here you can see the decrease in the frequency of thiophenolic SH, and the next one in the carboxylic group. So we know that C double bond O, the ester group gives the asymmetric and symmetric stretching. Okay, and at the same time, the carboxylic group is capable of having the new OH absorption, and it also available in the range 3,300 centimeter inverse, and we can have same time we can have the C double bond O frequency in the range 1,680 centimeter, and we can have the 1,668 to 1,600 centimeter, 1,671 centimeter inverse, and 1,419 to 1,420 for the symmetric and asymmetric stretching of COO minus. Okay, so this carboxylic acid group is capable of having the symmetric and asymmetric stretching. Okay. And after the deprotonation of the hydrogen from the carboxylic acid moiety, we have the variations in the FTIR value, that is 1,654 to 1,657 and 1,409 to 1,438 centimeter inverse. So the first one 1,654 to 1,657 is for asymmetric, and the later one is 1,409 to 1,438 is for symmetric. So if it is more 200, so that we are having the symmetric and asymmetric stretching in the COO moiety. And if the difference is not less than 200, not more than 200, we can have, it is not undergoing symmetric and asymmetric stretching. The COO moiety, the two oxygen available in the carbonyl compound, that is carboxylic group, is capable of having a bidentate donor site. Okay, and you can see the electronic spectroscopy. So from the with the help of the electronic spectroscopy, we can find out the availability of a charge transfer transition between the metal and the ligand. In some, whenever we have the back bonding, that is whenever we have the donation of electrons from metal to organic moiety, there we can have metal to ligand charge transfer. If we have the transfer of electron from ligand to metal, then we can have the ligand to metal charge transfer. So by recording the electronic spectra for the organic compounds, we can identify the availability of transitions. Here we are having the pi to pi star transitions in the range 255 to 298, and N2 pi star transition 340 to 426 nanometer, which is due to the azomethane group and also the benzene ring, and 254 to 473 nanometers. So this is due to the ligand to metal charge transfer. So whenever we have the availability of back bonding, that is whenever we have the donation of electron from the metal to ligand, then we can expect the metal to ligand charge transfer. This can be expected only in the case of cyanide and carbon monoxide, CO. Okay. So if you don't have the availability of cyanide and carbon monoxide, we can have the LMCT charge transfer. And after 400 nanometer, we can expect the DD transitions. So the electrons available in the d orbital of the metals, or the metal atom, are responsible for the transition. So next one is the NMR spectra. So here in the case of NMR spectra, you can see, let me go to the structure. So here you can see we have the methyl group, and here we are having the phenolic OH, thiophenolic SH, and COOH. Okay, and the remaining is a methyl and active methylene group, and here we are having one methyl group. Okay, so by considering the protons of the protons available in the functional group, and also by having the variations in the values, we can confirm the formation of bonds. So whenever we have the disappearance of phenolic OH proton, thiophenolic proton, and carboxylic acid proton, then we can confirm that the ligand is coordinated to the central metal atom through the deprotonation process. So we have the multiplets in the range 6.3 to 8.1 ppm. So whenever we have the multiplets in this range, we can have the peaks only for the aromatic protons, and in the case of 8.6 to 10.1 ppm, we can have the single peak for NH proton, and for CH2 protons, we have the peak in the range of 2.4 to 3.5 ppm, and for methyl, we have the peak in the range of 1.8 to 2.2 ppm, and we have the phenolic OH proton in the range 10.8 to 10.9 ppm, and in the case of thiophenolic proton, which is less than 4, there is 3 to 4. We can expect for a thiophenolic SH in the range of 3 to 4, and for a COH proton 9.6 to 10.8 ppm. So this is the NMR spectral value for the ligands. So here you can see, so this is ruthenium-3. So here the oxidation state of ruthenium-3, which is a paramagnetic in nature, and therefore we could not go for recording the NMR spectra for the paramagnetic complex. So we can go for the EPR, electron paramagnetic resonance, only for the paramagnetic material. If we use the ruthenium with the plus 2 oxidation state, we can go for NMR spectra for the ruthenium complexes. Okay, if it is in the plus 2 oxidation state. Okay, so out of 12 complexes, the 3 complexes are having the G value 1.9 to 2.2 with isotropic lines, which represents the intermolecular spin exchange. And in the case of another 3 complexes, which is having the different value, that is Gx is equal to Gy, and which is not equal to Gz. And then the remaining complexes are having the 3 different G values, which shows the magnetic anisotropy. Okay. And for one compound, we have recorded the spectra at room temperature and liquid nitrogen temperature. So in the case of room temperature, it shows a single value alone, and at the liquid nitrogen temperature, we got clear spectra with the hyperfine splitting. Okay. So next one we have the electrochemistry, that is the cyclic voltammetry. So the cyclic voltammetry explains the oxidation and reduction potential of the synthesized complexes. Okay. So here the oxidation and reduction of each complexes were characterized by the well-defined waves with E of values ranges from 0.3 to 1.25 milliwatt. So this is for oxidation, and for the reduction we have minus 3.4 to 1.45 milliwatt, and the electrode used is silver chloride. And for the 4 complexes, we have only the reversible oxidation in the ranges from 40 to 100 milliwatt, and one complex we have the reversible reduction peak at a 90 milliwatt, and another complex RuCl-PPH3 L2 shows only the reduction potential, and we observed that the redox couples with the peak to peak separation value del EP ranges from 120 to 790 milliwatt, revealing that the process is the best quasi-reversible, and which is due to the slow electron transfer. And we have the application studies. I have done the application studies for the synthesized complexes by having the doing the oxidation of alcohol. So here you can see I have taken the 2 substrates. One is benzyl alcohol and another one is cyclohexanol. Okay. So in presence of, so here we have the exact setup. So in this tube, we used to pass the molecular oxygen, pure oxygen gas. So instead of the using the oxygen supporting catalyst or oxygenating catalyst, we used only the oxygen gas. So we have taken the benzyl alcohol and cyclohexanol in the dichloromethane solution, and we have added the millimolar concentration of ruthenium catalyst, and then we started to stir the reaction mixture by passing the oxygen gas. And after continuously stirring for 6 hours, we derived the products benzaldehyde and cyclohexanone. So one is an aldehyde and another one is a ketone. So the product formed were quantified as 2-dinitrophenyl hydrazone. So this we done with the help of sintered crucible, and we compared the percentage conversion of the alcohols. So here in the case of using the ruthenium catalyst, which shows a better percentage of conversion, and also we carried out the same reaction without the presence of catalyst, and in that case also the alcohols responded to the oxygen gas, and in the case of having the ruthenium as a catalyst, the rate of conversion of the alcohol to aldehyde or ketone is greater than that of the empty reaction, that is without the presence of ruthenium catalyst. And next one we have the aryl-aryl coupling reaction. So this is nothing but the Grignard reaction. We have studied about the Grignard reaction in the schools as well as in the second year and first year chemistry classes. So here by using the
Dr. Aruna Shlam. We can't hear you.
We cannot hear you, please. We can't hear you, please. Can you check your mic?
my network connection is proper only. For long time or short time browser?
Yeah, now we can hear you.
Browser, excuse me. For long time it was not audible, or now only the interruption?
Just now, just now. Please carry on.
Yes, thank you, Professor. Thank you, Professor. So after the preparation of phenyl magnesium bromide, we added phenyl bromide along with the ruthenium catalyst. We have the formation of biphenyl. So the formation of a biphenyl as a product can be easily identified from the smell. So from the fragrance of the biphenyl, we can identify easily whether the reaction is carried out or not. And again, we have quantified the same reaction by the gravimetric method. And after the method, we used to complexes synthesized were evaluated against we have evaluated the efficiency of the ruthenium shift-based complexes against all those complexes and also with the reference complex. So here the ruthenium complex shows a better activity when compared to the other. And next we are
Professor,
going to have
please,
the
your voice is
unusual
conclusion side, because go to the conclusion, please. Your voice is not coming clearly.
Now, Professor, now it is okay or not? Professor,
okay.
it is audible now? Okay.
Yes, please carry
So now
on.
we are going to have the unusual behavior. Yes, thank you, Professor. So now we are going to have the unusual behavior of the copper complexes. So usually the copper alone exhibits the unusual when it is treated with the sulfur containing ligands. So here we can have the first case, that is the CuCl2 PPH3 twice. When it is reacted with the phenyl thiazomine carbazide ligand, you can see we have the formation of a complex. Here we get two copper central metal atoms, sorry, central metal ion. One is 3 coordinated and another one is the 4 coordinated. Okay, so this is unexpected formation of the complex, and it is reported in the possible mechanism for the formation of the copper complex. So this is related to the desulfurization process, which happening in the petroleum reservoirs is also playing a major role. So that is the base reference we have for these kind of reactions. Okay. So here you can see we have the CuCl2 starting. This is in the +2 oxidation state, and here we have only the sulfur moiety, and we have the initially we have the formation of the bond. The sulfur is capable of having the coordination carbazide connects the copper from the metal starting, and after the metals, and we get the and they get polymerized product, which was unable to recover as well as characterized, and we get this product, the copper with the the copper with the 4 coordinated sides, and again by having the elimination of one triphenyl phosphine, we get the final complex with the 4 coordinated and 3 coordinated copper, and it is the first reported copper complex which is having 3 coordinated side and a 4 coordinated side, and for this they reported the crystal structure also, and again they repeated the reaction to synthesize the same compound, but unexpectedly they received the different compound. So here you can see the triphenyl phosphine is represented by the red color one, and the copper is by blue, and you can see in Cl minus. So here the Cl minus is behaved as a mu3 type of ligand. So due to the availability of mu3 chlorine ligand, it forms a cubane type of structure, which is similar to that of the iron ferritin complex. So in the case of iron ferritin complex, there is an iron connected with the sulfur. So another type of different type of complex we have this one dissolves here. They have used the different type of metal precursor along with the additives. So here you can see CuNO3 3HO. Here also we have the starting with the +2 oxidation state. So automatically, whenever we have the reaction, the copper undergoes reduction and forms and gets converted into +1 oxidation state. So here also we have the reduction of oxidation state from +2 to +1 takes place. This we call as auto reduction process, and it is highly possible to predict that which material is responsible for the auto reduction of copper. Yeah. And here you can see, so in the previous case, here we had the fluorine, and here you can see SH. So this is another type of cubane. We have the SH which connects the 3 copper atoms, and finally constitutes a cubane type structure. This structure is also very, very due to the field of inorganic chemistry by considering the copper complexes. And they repeated the same type of, this is the possible mechanism for the formation of the copper Cuban structure. So here you can see we have the thiocarbamide, so which is got connected with the Cu1. So here the oxidation state of copper got reduced to +1, and again you can see we have the elimination of copper from this set. We have the formation of a bond between the sulfur and hydrogen takes place due to the availability of water molecules available from the copper starting. So the water molecules available from the copper metal starting hydrolyzes the S group and converted SH type of salt. Again, this on triphenyl phosphine migration insertion reaction. You can see we have the insertion of a triphenyl phosphine to the copper takes place, and finally we have the formation of a cubene type of a complex. And again, they repeated the same type of reaction with the different solvents, whether they arrive the reported complex or not. So here they received the different type of complex. Here also they received the different type of complex. So first they carried out the reaction in the presence of benzene and diethyl ether. Second, benzene and methanol. Third reaction, benzene and no benzene, no methanol or diethyl ether. They carried out the reaction in the presence of chloroform. Again, they received the different type of copper complex. So here you can see they solved the crystal structure for this cubene type. So here we have, so here you can see the sulfur is having the 4 bonds to donate 2 coordinate bond and 1 electronegative bond to the central metal atom, that is the copper, and another one is to the H+. Okay, and finally we have the cubene. So this is also very similar to that of the iron ferritin complex. So instead of copper, we have the, instead of iron here we have copper, and instead of other organic substance got attached to the iron, we have the triphenyl phosphine. And in the case of the third product, here you can see we have the similar structure.
Excuse me,
So
sorry for the interruption. Yeah, you have 2 minutes left. Thank you.
Ma'am, come again, please.
You have 2 minutes left, please.
Yes, please, ma'am. Yes, please. Okay. Okay. So here you can see we have the different complex. So here we are having the SH instead of the fluorine. So here, instead of sulfur alone, we have the SH, and here this copper is 4 coordinated, and here it is 3 coordinated. This is also a very new structure. And let me skip this also. Okay. If I continue, means it will take more than 20 minutes. Finally, let me thank the management of Savida Institute and also the Professor Muhammad. He is the concerned who interacted with me for this opportunity. Thank you, sir. And I once again I thank the management of Savida Institute. Thank you, professors. If you have any doubt, you can ask me, because this is a traditional field.
Thank you very much. Thank you, Dr. Arun Ashlam, for being with us today, and thank you for the nice talk. Let's see if anybody have any question or any. I guess there is no question. So thank you very much. Thank you again for being with us today. At the end, thank you. At the end of this session, thank you very much for each one of you, especially for the attendance, for everyone for sharing your expertise and knowledge with us. Thank you for the audience for being with us today. Just a reminder, if you want to get the attendance certificate, please complete the application on the link which located in the chat box. And we will have a break until 1 p.m. So thank you very much.
Thank you, Professor.
Assalamu alaikum wa rahmatullahi wa barakatuh. Good afternoon and hello everyone. This is Nuha Al-Jabr, Assistant Professor in Applied Mathematics in the College of Science, Imam Abdurrahman bin Faisal University. You are welcome at the second session today in the webinar, which is about the mathematical modeling for sustainable development. And first of all, I would like to express my sincere thanks to our college and Imam Abdurrahman bin Faisal University to organize this webinar. And also, we immensely appreciate all the speakers for their valuable contribution and sharing us their knowledge and research. Okay, now let me proceed to introduce the first speaker, Professor Azayez. Professor Azayez Mejdi, he is a full professor at Purdue University in France. He is a full professor of mathematical engineering at the Polytechnic Institute of Peru since 2001. He is expert in many agencies of research. His research activity has been motivated by modeling and simulation, natural and industrial problems, and application. And his topic today is about reduce order strategy to solve Allen-Chan model. You are welcome, Doctor, to start your talk. Hello, Doctor. Hello, Dr. Azayez. Sorry, we cannot hear you, Doctor. Dr. Azayez, can you hear us? You are welcome to start your presentation, Dr. Azayez. You can show your screen now. Sorry, Dr. Azayez, we cannot hear you. Can you open the mic, please? Hello, Dr. Azayez. Sorry, your voice is not clear. Yes, Dr. Azayez. Do you hear us? Sorry for inconvenience. Shortly we'll be with you, inshallah. Hello, Dr. Nabil, can you hear me? No, Dr. Nabil, I couldn't hear you.
How do we do? Is it okay?
Yeah. Now it's okay.
Ah, perfect. Okay, wonderful. Let me share the screen. And do you see the screen?
Yes, doctor.
Do you
It's
see my
clear now.
presentation? Okay, wonderful. Okay.
Yes, you are welcome to start, Dr. Azayez.
Thank you. I'm sorry for this. Some kind
That's
of
okay.
technical problem. It looks that we are not, after 2 years of using this material, we are not still able to run without any problem. Okay, thank you for the invitation. And let me introduce to you a very recent work that I am achieving with the collaboration of 2 professors who are from China, from Xiamen University, is Professor Xu. The other colleague is from Sevilla University from Spain, is Professor Chacon, and our former PhD student, Mr. Hu. Okay, the subject is, as mentioned in the title, I would like to share with you some experience about how to reduce model when we are interested in some kind of problem that we call Alenkhan model. And Alenkhan is one of the famous way to model phase field, let's say phase field model as well. I will start by recall to some of you what is Alenkhan model and why we are interested in. And after I will give you our way to start model reduction, and I will introduce some material to help us to ameliorate our way to use reduced model and to enrich it. Okay, let me start, as I said before, with what is Alenkhan model. We are interested in 2 phase field, one in, let's say, solid and the other is liquid. It is one way. We have several ways to do it, and one way is to go with this kind of method, what we call phase field. And you can see at left, let's say, for example, we are in solid, and at my right in liquid, and in between we have some length of epsilon, which is the phase transition, let's say, region. And this is measured by epsilon, and the function u will be equal 1 in one phase and 0 in the other phase. And usually we couple this this model of phase field with, for example, here I'm going to share with you phase change modeling, and we have T, the temperature, U is the phase field I'm interested in, and you can see that we say that when the temperature change, we can move the phase field. When the phase field change, we can update the conductivity, as you can see here. I mean, the conductivity depends on the value of phi, and it means when we adapt ourselves to the new region that is progressing in time. The coefficient that we see here, tau, L, and K, they are very, very classic when when you work in this field of PCM. And this is an example rapidly made by one of my students. We can see that the phase field, blue, it is going to be, let's say, solid, and red, liquid, and we are solid. The solidification works well, and we can see that we have some kind of agreement between the progress of the temperature and the progress of the phase field. This is an example to show you that it's very, very interesting to handle this kind of technique, what we call phase field, and especially Alan-Kahn. Let's go back now to our interest. I mean, the previous example is related to one material. Let's suppose that your sample, the material, can be not one, but you want to try to be able to simulate for very, very different value of characteristic value of the material. To explain this, let me fix the objective. Let's read together what is 1.2 equation. We have the Alan-Kahn model, and inside the Alan-Kahn model, I have this coefficient, and I decided to play, let's say to work on the possibility to solve this problem for almost everywhere beta in this sample. I mean, I will fix beta minimum, beta maximum, which are the coefficient minimum of maximum that can takes beta. And let's say that I would like to generate one way to compute rapidly for all the beta. I mean, I am able to make some kind of dictionary of some kind of data. If someone comes to say, okay, can I have some idea about this material? I'm not going to solve it. I can maybe find the solution in my data. And for this, I have to produce one way to be able to answer rapidly. Please keep in mind that usually when we solve a partial differential equation, we have the space, which is x. We have the time, which is time. And in my problem, I would like to add another one, which is beta. Okay, so time will be evaluated between 0 and capital T. X will be in my domain omega, which is going to be the square for the application, and beta will be in this interval beta m beta capital N. And I choose this coefficient. I can also maybe to repeat this exercise by considering this parameter, the conductivity, as a new parameter. Okay, so once again, remember that U is the phase field. It will take two value, one on -1. I have the Gansberg-Londo double well model, and this is not the unique choice, but for our application, it is a very sufficient one. And for my way to approximate this problem, now I'm speaking approximating in time and space, I will split with the classic way the nonlinear term capital FU in a convex and a concave contribution. And for my example, I will fix convex part to be like this one. And of course, the concave one will be this one. So by the way, the derivative is going to be also the derivative of each contribution. So keep in mind that I have convex, and you know that when we use Emacs, what we call implicit explicit scheme, it means that I would like to approximate the convex part by implicit way and concave part by explicit way. The scheme remains unconditionally stable. This is very old and very well-known result. So now let's progress. Let's consider the classic Sobolev space to write the variation formulation. Okay, this is interesting because I have two equations, 1.5 and 1.6. 1.5, it means that I can run for almost every beta this problem. It means that I take beta, I solve time space problem, I change beta. This is, and I mean, I have to solve this variation formulation for each beta. Another way is to consider the problem in the hypercube. I mean, to say, okay, let's consider that my variable, my unknown u, for instance, u bar, will depend in time, in space, and in beta. And it will progress, it will leave in some L2 gamma of H1 and also time. And you can see that I can now I can consider, let's say, an extension variational formulation. I have to integrate in time, in space, and also I have to integrate in parameter space. You can see that my test function is also will progress depending with gamma as well. So, of course, I'm going to, with one cube to a hypercube. By the end, I will reduce in the hypercube, so I will be more fast by the end. Okay, I need also to approximate in time. I can present the same work using many other approximation, like explicit, like SEVs, or I don't know, so much method. Let's go with this one. And you can see that I have a first order scheme. I will implicit the convex part. I will explicit the concave part. And as I need also to approximate in space, let's go with finite element, but I can go also with any, with your favorite method. This is some kind of detail. Okay, for me, it's going to be finite element. And the classic may be P1 here, absolutely P1, and the numerical part is going to be P1. And let me once again say that since it is nonlinear, of course, the convex part, remember that it is u about u power 3, u power 4, I don't remember. Now it means that I have to transform, to change the problem and to consider it as a minimization of this functional g that you can really, it's easy, it's an exercise to identify it to be exactly this one. So the new problem is now to look for the maximization of this function that I give here. You can trust me, it's correct. And okay, now how to write our reduced model. Let me start with something that we consider that we already on offline computed all the phase field solution for many beta. So I have in hand this data, and from this data I would like to apply some kind of correlation, and you can see this is correlation that's going to be something that I will produce in space. Okay, so I produce in space, so I can consider the adjoint of it. But what can be easy for you to be fixed and to fix it in our mind, let's consider this kernel K, and let's consider that from this, for each 2 points of omega, x, and epsilon, I correlate the solution already computed for all the beta and all the time. So this is, we have to make some many scalar product, and by the end I have this matrix. It's going to be from the discretization point of view, it will be a matrix. For now it's an operator, and it's very easy to see that the operator is called symmetric, and it is really something that can be we have the eigenvalue positive, and we have an orthogonal basis which is obtained by the eigen function correspond to eigen. So by 1.14 resume the situation. So we are able, once we compute this, we are able to have the matrix and to produce this eigenvalue. And I have some results that due to KL, this is what we call Carnot UV expansion. And we have almost sure to produce this eigenfunction and this eigen singular value, as you can see here. And please, this is the fundamental result. So our solution, which depend on time and space and parameter, can be expanded by the tensorized product between space and function depending on time and beta. And I'm going to keep only the information that what's here. I mean, okay, I have data, I correlate, I compute eigenvalue, singular value, sigma m. From this, I produce the eigenfunction, and I keep only the eigenfunction that I will call it phi m. Okay, and if I truncate, if I denote it by um, the expansion limited to capital M, I have this very classic result, which telling us that the error between the data, space, time, and parameter minus the data truncated and given by this expansion is the error is given by 1.15. I mean, it's very interesting because if the lambda decreases rapidly to 0, it means that the approximation will be very nice. Okay, so we try to continue. We have the data, we correlate, we compute eigenfunction in space, we keep them because it's going to be our reduced basis. This is our first reduced basis. The reduced basis will be the subspace or the space spanned by phi1 to phi nr. Nr will be decided by the, let's say, the value of the eigenvalue. I mean, you produce some eigenvalue and you consider that start from 1 to 0, and I can decide that I will retain only the eigenfunction corresponding to those eigenvalue which are bigger or equal to some tolerance that I can fix. Usually we fix tolerance like 1 to -3 or -4, depends on the problem itself. Okay, so once we have this new space, which we call reduced space, we rewrite the problem, and we consider that the new unknown, it is for one beta. Now I computed for many beta, and I would like now to compute for new beta. And to compute for new beta, I will consider the expansion, the solution to be equal to this 1.16. And so let's say that I put this unknown in the variation formulation that I already presented to you, approximated in time and space by finite element, and the test function are not going to be finite element test function. No, it will be test function coming from the basis, reduces basis eigenvalue, eigenfunction, and 1.17. What you can point now that the dimension of this problem is nr. I mean, we have nr unknown to nr equation, and nr is supposed to be small. And in practice, I can ensure that when the problem is regular, when everything runs good, and I will see together for the numerical part, that it's going to be something like that. We have to solve system of 10 equation, maximum of 10 equation for 10 unknown. Okay, once we do this, I rewrite the minimization problem, but it's in the reduced basis, and I can solve this. Okay, now imagine that you don't have the full model. The full model is the model that you are solving with finite element and finite difference. We have some kind of reduced model. This reduced model is based on your reduced basis that you computed thanks to the offline simulation. How can you trust? How can you trust? I mean, you come with a new beta. This is a new parameter, and you want to solve it. You solve it with the reduced model. You don't want to solve it with the full model. But you want to have some criterion, something that help you to say, okay, I trust the solution coming from the reduced model without traveling to the full model and without running the full model, because the full model is expensive. I want to stay with the reduced model. I want to try for the new sample, for new material. I want to decide if the solution is good enough or not. To do this, we have to introduce this wonderful equality 1.20, which is the residual. This residual, as we can see, is based only in your reduced computation, and you have to test against the finite element. This is what we call the residual that I'm going to use. I have two parameters, two coefficients that I introduce here and here. It will be useful, okay? This is a posteriori. I think I don't have time to enter into detail to this theorem, but this theorem will explain to you the following thing. Okay, with the numeric result, you will understand better. Okay, let's go. Let's do the strategy. I have many beta. I start with consider discretization, because we are not going with the continuous interval. So we make some kind of selection, like for finite difference. Okay, I will deal with all this beta. I have 1,000, and what I'm going to decide is to take some of this beta to solve it with the full model, and after to make my basis and to solve with the new. So I have what we call simulation, sample, simulation, and target. Okay, let's read this. Compute the solution using full order model, finite element difference model. Okay, for each beta I start, and I decided I start with 1,000, I will compute for 10. From this 10 parameter, I will produce my basis. My reduced basis is going to be an R. An R is supposed to be very, very small with respect comparing to the N that I try to solve. And now what I am going to do is to to create my reduced order model and to solve for all the new beta for what I call the target. And for each new solution obtained by reduced model, I will compute this coefficient. Okay, this coefficient is given below, and among all this coefficient obtained and computed for each new beta computed by the reduced order model, I will consider what is the worst one, what is the one that makes that this error is the maximum. And this maximum, I will consider it as something that I have to enrich for the reduced order model. Okay, my reduced model is with the dimension 5. I have 1,000 parameter. I will solve the 1,000 parameter new parameter thanks to this reduced model. I have this coefficient very rapid to compute for all the new solution, and I will select the worst one. The worst one is the biggest one. It means that my reduced basis is not able to represent this, and among all, this is the worst one. Okay, so it means that it's time to enrich my basis. It's time to open the full order model to solve a new solution corresponding to the worst situation, and to recreate the new basis, and to go from dimension 5 to dimension 6. And once I do this, I have another reduced model, and I try to run all the parameters. So usually from the practice point of view, after 5-6 enrichment, we are able to have a situation for which all these coefficients are very small. Let me, this is the coefficient. This is the coefficient. This is the coefficient that corresponds to the a posteriori estimator error. It is the norm of this, and this comes from this equation. It's and believe me, it's an explicit computation. What is interesting that, let's go with this example. This example that I start with a phase field, which is something that corresponds to 1 inside the disk and 0 outside. And I ran for a sample. I decided I have, let's say, something like 30 parameters to compute. I will compute in the beginning only 1, 2, 3, 6. I produce full order model solution to only these 6. So I ran 6 solutions. They are what you call, they are good solutions in the sense that it comes from finite element and finite difference. That there is no problem of model reduction. And from this, what I'm going to do, I'm going to write a reduced order model, and then I will solve the rest of parameter, or the remaining parameter, thanks to the reduced order model, and I will run my estimator, and I will see what's happened. Okay, this is, first of all, this is when I compute for example, for one of the solution. This is just to show you that that I have eigenvalue of my model, and I have the error between the estimate, let's say the estimator, and the finite element solution, the full order solution, and the reduced order model. We can see that it runs good. Better to focus on this. The blue one, it is the measurement, the numerical measurement of the estimator. The red one, or I don't know which color, is the error between the solution, finite element, and the reduced one. And you can see that when the blue decreases, I mean, every time here we have the order, I start with 5 bases, 5 eigenfunction. I produce my reduced order model, and then I run my estimator. The estimator say, oh, guy, you have to add another eigenfunction. So it means we have to add another eigenfunction. I add another eigenfunction. I see that the new error coming from the reduced order model, when I run all the parameter, it's better. So what is interesting that the estimator, a posteriori error estimator, decreases to 0. In the same time, it asks us to enrich, and in the same time, the error between the full model and the order model decreases. This is what we call an efficient estimator. An efficient estimator is something that tell you, no, you don't need to enrich. Everything runs okay. Your reduced order model is able to produce all, to reproduce, to give you the information of the new parameter. And when it's not possible, they will ask you to enrich. And when you enrich, the new approximation is better. So you have convergence between the full model and the reduced model to 0. And in the same time, you have convergence of the estimator. And this is, for the moment, we proved that the estimator from the mathematical point of view is something that go to 0 when you have the right condition. And we proved that the error between the reduced order model and the finite element model go to 0. And we are working on the, let's say, the velocity of convergence. I mean, with respect to the regularity of the solution that we want to simulate. This is, I think, the end of the talk. It's really, really recent work where we are really now trying to couple this result, which is only dedicated to phase field, with something which is my goal is to couple it with the temperature and to be able to simulate different scenario of phase change material. And you know that behind this we have the application of heat storage based on the phase change material. And this is a very, very recent work. And we have some other results that maybe I will have the possibility to present later once the PhD thesis will progress more. This is the end of my talk. And thank you very much once again for your invitation. I hope that it was a minimum clear. Thank you.
Thank you very much, Professor Azayas, for the nice and interesting topic. And let us now move to the questions. Any questions? Dr. Nabil, do you have any questions?
Do you hear me?
Yeah, we do.
Yes, yes. Your voice is clear.
I was fixing my my microphone. No question, but just these computations are made in 2D, Majdi?
Yeah, no. Very good question. This computation is made in 2D, okay? And yes, in 2D. As you can see, we have, it's really work in progress, but because we have, I asked my student if it's possible rapidly to compare something that it's very important for you, in the sense that how CPU time we win. Okay, I mean, let's try to see that I'm using full order, the full order model for all the parameter and reduced order model, and what is really the advantage and the gain in time of CPU time. I mean, are we really producing some kind of code that produce a solution in real time, or the reduced order model needs many time as well? So you have full order finite element. In instance here it is free FM, and you have your reduced. If free FM takes 1 day and the reduced model takes let's say 18 hours, I think it's not interesting. Our objective is to be able with the reduced model to really answer rapidly, okay? And for the moment we don't have this possibility to present results. So we are working on the optimization of the code. And one of the reasons, Nabil, comes from the fact that the approximation we use it is implicit for the nonlinear term for the convex part, and it seems that we have some troubles with the minimization.
Okay, I understand.
Sorry.
My second question is if you go to the 3D case, I think that all the principles are the same. And does the estimators are difficult to have in 3D, or it's the same difficulty like in 2D?
It is the same formula. It is the formula. It will be, I'm afraid, maybe it will cost, because as you can see, let me tell you something. The only thing that you have to, the only point that you have to solve when you compute the estimator, okay, is to inverse mass matrix, a mass matrix, okay? And for the moment, we really invert it, okay? We are, normally we have to go with some kind of mass lumping or to work on this point to make it possible on 3D, okay? The only difference of cost will come from how to compute the inverse of the mass matrix in finite element. Okay. And the rest, it is an explicit computation. We have to make scalar product of the data of the gradient, and it's fast.
Okay, thank you, Majdi.
Thank you, and sorry for the starting. Some problem.
That's okay, doctor. That's okay.
Notice that I have the same problem with my first computer.
Okay.
Thank you again, Dr. Azayez. And now let us proceed. Thank you. You are welcome, doctor. Now we proceed to the second speaker, Dr. Nabil Kamati. He is a fellow professor at Department of Mathematics and College of Science and Imam Abdurrahman bin Faisal University, Saudi Arabia. And his topic is about on the Schwarz method for the ED current problems. Hello, Dr. Nabil.
Okay,
you can share us your presentation, please.
My slides, yes. I'm not sure that
yeah, it's clear now.
I'm sorry, but
Your presentation is clear, Dr. Nabil. You can start your talk.
I can start now? Okay, thank you. Thank you very much.
You are welcome, Doctor.
Okay, then I'm going to present a recent work on about the Schwarz method for the eddy current model. This is a joint work with Faten Jlassi from University of Compiègne and my former student, PhD student, Anis Mohammed at University of, who is now at University of Tubergen. Okay, what are eddy currents? Eddy currents are loops of electrical current induced within conductors by changing magnetic field in movement, according to Faraday's law. And there is a lot of applications and for eddy currents, like electromagnetic braking, repulsive effects, identification of metals, and vibration, sensing, and so on. And like we are going to see, the problem modelized with partial differential equations is a problem settled in bounded domain. And to solve it by numerical method, like finite elements, for example, we need to truncate the domain into a calculation domain. Let's say that sigma is a fictitious boundary who is enclosing the interesting region. Okay, and the question is which condition, which absorbent condition we can set to close the problem. And for that, we will use the coupling method, the coupling variational problem into a restricted truncated domain. And we will obtain an equation set in a bounded domain, and our aim is to solve this equation by an iterative algorithm. In fact, we studied these iterative algorithms the last years, and the idea is to make an interpretation of these algorithms under a Schwartz method. And this fact allows us to make a convergence analysis and to prove an exponential convergence for the iterative solver. Okay, and a lot of researchers work on this problem, and the most popular method is integral equation. And we can see the work of Habib Ameri and Annalisa Boufa, Nedelec. And our choice to solve this problem is to use a method that was settled in the late 70s by Adrien Jamy and Marc Lenoir. And we will use this method and prove its convergence when we use it under an iterative solver. On artificial boundary conditions, we can see also the work of Hussam Haddar and Ziang on eddy current problem too. And for results about Schwartz method, we can refer to the work of Paul Williams. And we are more recent works on this topic. For our work, we need these notations. I make a reminder about L2 is the square integrable complex valued function with its norm, H1, the subleft space, and H1/2, the traces over gamma, and H-1/2, the dual for H1/2. Okay, and to the modelization of the eddy current, I need just to say that the basic equations are Maxwell equations, and we use a source current density J, capital JS, under this form, and then we can write the magnetic field and the electric field under most simply expression, like we see here. And they use a scalar magnetic potential, who is the solution of problem, not noticed here, problem 4. And we close the equations with the condition at affinity that is coming from the Biot-Savart's law. And then the model that we are going to deal with is this problem set in R2, bidimensional problem, okay, where we have a term here in divergence and a term in phi. Okay, let's just say that the first term here that we see here is only on the bounded domain omega. Okay, chi omega is the characteristic function over omega. And also for the right-hand side, okay, is equal to 0 out of the domain omega. And out of the domain omega, the constant mu, the permeability, okay, is constant. Then this term give Laplacian here, okay, and we can see that the equations are elliptic. This is then the most appropriate variational framework, okay, and with the corresponding Hilbertian norm. And then, like I said before, to solve this problem that is set in a bounded domain, I need to truncate the domain. Then I have a permeability that is variable into the domain omega here, and mu is equal to 1 out of the domain. And I choose a boundary sigma that encloses the boundary domain omega. And now I'm going to write the variational formulation and solve it, for example, with a finite element method. To write the boundary condition, I need to use an artificial condition. And it's an artificial condition that write an integral representation out of the domain, okay, with thanks to the green function J that is well known in 2D and 3D. And here is the expression of J in 2D. And here G and I is the normal derivative with respect to the normal of the boundary gamma. And here this term, of course, is a single layer term, and the second term is a double layer term. And to write the boundary condition, I have just to derive, to apply the normal derivative to this first equation on the boundary sigma, and I get this term, and I will use this condition as a boundary condition. Okay, and now the boundary value problem is given with the first equation. It's exactly the same like in the initial problem. We have just write this equation on the truncated domain omega sigma, and we have the boundary condition, who is a non-local condition but written on the boundary sigma, okay, thanks to the single and double layer potential, okay. And then in our work, omega sigma is a connected domain. This problem is equivalent to the complete equation 5-6 seen before, and the variational space is H1, okay. And if I write the variational formulation, I get this equation, okay. Here we have a mass term, stiffness term, okay, and a term that couple sigma with the boundary gamma, okay, with the double layer potential and second layer potential, okay. And here the right hand side leave only on the domain omega, the conductor. To solve this problem, we solve it by iterations. Why? Because when we write this iterative method, at each iteration we have a local condition, and it means that after discretization by a finite element method, for example, okay, the matrix will be sparse. And it's not the case, of course, when we applied the finite element method for this problem. Okay, it's why we proceed by successive iterations. Okay, and our problem, of course, is to prove the convergence of these iterative method. Okay, and then after writing the corresponding variational formulation corresponding to this problem, we get this variational formulation when we have here the stiffness matrix and the stiffness term and the mass term, of course. Okay, and now the integral term is on the right hand side. Okay. This work is a continuation of an old work where we prove the convergence for the Newman condition. Okay, but in our first work we prove that the convergence is given only when sigma is reasonably is located far from omega. Then we need a distance between the two conditions. And in this new work, we prove that we have an exponential convergence of the algorithm for any distance between sigma and gamma. And the only condition that we need is that the intersection between sigma and gamma is equal to the empty set. Okay, it is no elements in the intersection. These are disconnected. Okay. How we prove this exponential convergence? We split the problem in two parts, exactly like in the Schwarz domain decomposition method. Okay, and then we need two partial solutions. Let's say, and let us introduce a sequence WM. Okay, for the odd term. Okay, we say that omega 2m plus 1 is given by the integral representation, and for the term 2m plus 2 is equal to our solution phi m plus 1. And then it's equivalent to say that W2m plus 1 is solution of this problem. Here we have the problem at the outer domain, but completed by the same equation in the inner domain. And here we have the gap or the jump on the boundary gamma is equal to the solution at the previous iteration. Okay, and the gap or the jump of the trace of the function is equal to the trace of the opposite of the trace, of course, of the solution at the previous iteration. And we have the same condition at infinity. And for the even term, W2m plus 2, okay, it's exactly the same equation that we have to solve. Okay, the region is that W2m plus 2 is equal phi m plus 1. Okay, and then we have this equation. Okay, let's say we can see easily that in fact the solution of this problem is exactly given by this integral representation. Okay, but here it's just a way to set our problem under a Schwarz formulation. Okay, and it's what let us prove the convergence of our algorithm. Okay, and then we can set this theorem. Okay, how much time I have, please? Okay, then
yes, Dr. Nabil, you have almost 5 minutes.
But we start 10 minutes later. How can I have only 5 minutes, please?
Okay, I'm so sorry, doctor. So
okay, thank you.
You have 10 minutes. Sorry for that.
Okay, thank you. The sequence WM converge to the solution phi, okay, in this sense. And then we can prove the convergence of the sequence phi m to phi in the H1 norm. This is then a first result, and the proof needs to introduce the error between phi and ym. Okay, and we can see easily that the error at each iteration, in fact, is solution of the homogeneous equation. We change only the right-hand side. Okay, and here we have the connection between the odd term and the even term. Okay, and like we see here, e to m, the odd term are in R2. Then we need to extend the function e to m by this way to have for the even term. To have for the odd even term, yes, for functions that are set on the R2. By this way, the odd term and the even term are defined on R2. And the sketch of the proof, okay, needs these three lemma. The first one is a condition of stability. The second one is to prove that this sequence is square summable. And the third one, okay, is also a summation of square summability for this sequence. Okay, and then we need to prove the boundedness of this term, okay, and finally we get this estimation, and by the lemma 3, 4, and 3, 2, we can conclude. Okay. Okay, here we proved a convergence, but we can do more and prove an exponential convergence and get the rate of convergence. Okay, what is very important for us. Okay, and how we do that? We write what we called a Steklov-Poincaré formulation. It means a formulation set only on the boundary sigma. And for that, we split the solution into, we write that solution phi is equal to this summation, where phi underscore is defined by this term. Okay, here how we just remove this expression, okay, to get this problem linear with respect to the right hand side f. Okay, and theta is just, okay, the difference between phi and phi underscore. Okay, and if we set lambda equal the normal derivative of theta, we can prove that lambda is solution of this problem, and this problem is set only on sigma. Okay, and then here, here the operator a sigma is defined by this integral representation. Okay, and j, the right hand side j, is defined here. Okay, and then we can show that theta lambda is the solution of a problem, a Newman problem, okay, where lambda is the Newman boundary condition on sigma. And what is interesting here, okay, is that formulation allow us to prove some good properties for the operator a sigma. Why? Because, of course, here we can solve this problem by a iterative method, a Richardson method. Okay, it's just a fixed point or successive iterations, okay, applied to this problem. It's a fixed point problem. Okay, and then we can define the sequence lambda m plus 1 equal a sigma lambda m plus j, and lambda m we can prove very easily that lambda n is the Newman series, okay, with the operator a applied to a good initialization lambda 0. Okay, and when m goes to infinity, I have this expression of lambda. And what is important here is that we can prove that the operator a sigma is contracting. It means that the spectral radius is lower than 1. Okay, and that we have this, then consequently we have this approximation, okay, for any this okay, this inequality, and this let us prove the exponential convergence. It means that the error lambda minus lambda m at the iteration m is bounded by a constant who depends from the initialization to m, where tau is given by this inequality. And then we can conclude a theorem of exponential convergence for the sequence Wm, okay, with to the rate of convergence that is given by the operator A sigma. Okay, I will conclude now with some numerical results. Okay, for the numerical results, I will show some analytical computations and numerical computations. And for analytical computation, I will consider a disk, okay, where I can have the exact solution. And for numerical computations, I will also use a disk, okay, to be able to compare the result to the exact solution, okay. And I will consider a more complicated geometry with two disks, but we can also, in this case, build an exact solution, okay. And it allows us to compare the results of convergence to the exact solution. And for this study, for the numerical study, I introduce a Fourier condition, okay? And here you can see easily, of course, when beta is equal to 0, that I have our Neumann condition, okay? And the result that we have is available only for Neumann condition, okay? Let me mention that for the Fourier condition, the only proof that we made is that the algorithm converges for sigma far from gamma, okay? We know that there is a condition to have convergence for beta, and for the Neumann condition, the convergence is obtained for any position of the boundary. And okay, and then for the first example, I have this geometry, okay, and I compute analytically, I calculate analytically the coefficient of attenuation. It's for any mode. I make the expansion on modes for the solution, and it's the error, the ratio of the error for any for each mode. And here it's a plot of this coefficient, okay, the convergence rate for each mode. And what we see here, okay, white points represent the Neumann condition, and black points represent the Dirichlet condition, okay. And we see easily here that the ratio, the coefficient ratio of convergence are smaller for the Neumann condition, what proves that the convergence will be better for Neumann condition. And the second remark here is that for the Dirichlet condition, sometimes, okay, here we can have a coefficient ratio that is larger than 1, what proves that the algorithm do not converge for the Dirichlet condition, okay. Here, it's numerical computation obtained with the C++ platform called XLife++, and the meshes are obtained with Gmesh. And here we plot the convergence rate for the L2 norm and H1 norm. And here, for the picture at the left, the distance between gamma and sigma is very small, okay? And we see that we have a good convergence. And of course, here, the curve with black points, it's for a value of beta that equals to 0. It means that we have Neumann condition. And here we see the good convergence for the normal condition, but for the here beta equal 10, we are almost close to a Dirichlet condition or Fourier condition with beta equal 10. Okay, the convergence is not very fast. Okay, then we see here the good property of convergence for normal condition, and here it's the same computation but with a distance between sigma and gamma that is larger. Okay, and here we see that the two algorithm of the Neumann or Dirichlet, okay, give good results. Here we have this shape, then we have two disks, two not connected disks, and we show for some values here for beta equal 40, beta equal 10, that we have a good convergence. Okay, and the second graph here, it's another value for beta. Okay. Okay, here it's for beta equal 3 for Dirichlet and for Neumann condition. And the last numerical results here we have a distance. We have the convergence according to the distance between the two domain gamma gamma left and gamma right. Okay, and here we see that when D increase, the convergence is faster and faster. And as a conclusion, we say that here we proved the good properties of convergence for a Neumann condition for the Schwarz method, and what is interesting to say is that this method can be coded on any finite element code to solve unbounded problems, even if your code is a code that was implemented for just bounded domain. Okay, why? Because with just the corresponding right-hand side, you can change the problem into an unbounded problem. Thank you very much. And
okay. Thank you very much, Dr. Nabil, for being with us today. And actually, it was very interesting and nice talk. So now, if we have any questions. Any questions for Dr. Nabil? Okay, thank you very much, Dr. Nabil, again for being with us. And
thank you for the invitation.
You are welcome, Dr. Nabil. Okay, now let me proceed to the third speaker, Dr. Viswanathan. He is Research Fellowship and Offshore Extreme Technology Industry Academic Cooperation Research Center in Korea. He was in the position of a foreign professor to teach engineering, mathematics, and mechanics in the Department of Naval Architecture and Ocean Engineering at Inha University in South Korea for 3 years. His area of interest includes vibration of composite plates and shells, fluid structure interactions, fluid mechanics, and the numerical methods and analysis. And his talk today is about a free vibration of layered truncated conical shield filled with quiescent fluids. Okay, Dr. Viswanathan, you can
thank
start
you.
your talk. You are welcome.
Thank you so much.
Can you share your screen, doctor?
Yes.
मेरी थोड़ी सी
Yeah,
अभी
clear
इस
now.
बंदे के बाद प्रेजेंटेशन है
Is it okay now?
कॉन्फ्रेंस में हाँ
Yeah, it's a clear, doctor.
क्लास वो खत्म हुई चीजें भी बड़ी
Are
मुश्किल
you
से
seeing the slide? Hello?
Yes, we are. Your presentation is clear, doctor. You are welcome to start.
Yes. Thank you so much, madam. So thank you for your invitation to present the paper in your webinar. Now, my title is Free Vibration of Layered Truncated Conical Shells Filled with Ocean Fluid. Yes. So the presentation outlines the introduction. In the introduction, the application of shell structures and about the shell theories we are going to do. The mathematical formulations. This is the mathematical model of the shell structure and the fluid term, how it will involve coupled with the structural equations, and how to solve the equations using the numerical method, that is one called the spline function method. Then results and discussions. So then we solve the equation using the numerical techniques, and we compare the study and analyze the results and the conclusions and references. So the introductions. So this structures, composite structures, it is useful in this, widely used in many structures associated in the field of like shipbuilding, aviations, missiles, and rocketry. Composite structures are being increasingly used because of their possible higher specific stiffness and strength, and they have the better damping and shock absorbing characteristics compared to the homogeneous materials. The use of the lamination for the structures leads to the design with the maximum reliability and the minimum weight. This problem is solved using the classical shell theory. What is the classical shell theory? First we see here. This was originally introduced by the Laws. It is called the Laws first approximation theory in 1888. Here neglect the shear deformation and the rotary inertia. Straight lines perpendicular to the mid surface before deformation remain straight after deformation. The transverse normal do not experience elongations. Normal to the mid surface remain perpendicular to the mid surface after the deformation. So the mathematical formulation. So here the figure you can see that layered truncated conical shell element of the constant thickness. Here that this is given. This is the shell element. This is the conical shell. This will be the thickness of the shell. This is the thickness. Here there is a layers. This is consists of the many layers. We have to assume these consist of many layers. Each layer is assumed to be the homogeneous. So they are all the homogeneous, linearly elastic, and which is called the materials may be the isotropic or especially orthotropic materials can be used to this structure. Here this RA and RB is the radius. This is the RB and RA, the radii of the cone at its small and large ends. This is the length of the cone, L equal to B minus A. This is the origin we take from here, the length A, from here this is the length B. So L equal to B minus A is the length of the cone along its generator. The orthogonal coordinate system x theta z is fixed at its reference surface, which is taken to be at the mid surface. This is the mid surface, reference surface. This is the middle surface. and the UVW are the longitudinal circumference transfer displacement. So this is the thing. So we take this is the U, this is the U, this is the W. So here you can say Z. So Z, and this is the theta. This is the circumferential node. Circumferential means this will be like this. So here this V, this is the V. U, W, V. It is the circumferential direction. The radius of the cone at any point along its length is R equal to X sin alpha. So the radius of cone anywhere, it generally we can call R equal to X sin alpha. The radius at the small end of the cone is A equal to A sin alpha. Here, here, A sin alpha. Here, this is the B sin alpha. The equation of motion of truncated conical shell included fluid. So this is the equation we derived using the Hamilton's principle. We take the equilibrium equations. The element is in equilibrium position, and we will derive the equation using the Hamilton's principles. So we get the equilibrium equation of this one. This is the for conical shell. This is a truncated conical shell. Here the terms nx, this nx, n theta, nx theta are the force resultants, or we can call stress resultants. Mx, m theta, and mx theta are the moment resultants, and rho is the pressure of the fluid. We will call pressure of the fluid. Applying Low's first approximation. Now this is the first equation. We have the equilibrium equations, the governing equations. Now we have to substitute in that equations all the parameters and the variables, everything. The first we take the strain displacement relations of truncated conical shell. So this is the strain displacement relations: epsilon x, epsilon theta, gamma x theta, kappa x kappa theta, tau x theta, and psi x psi theta. So here we can call epsilon x epsilon theta and gamma x theta represent the normal and shearing strain of the reference surface. Kappa x and kappa theta represent the changes in the curvature of the reference surface during the deformation. The quantity tau represents the twist of the reference surface. This is the tau, tau x theta, twist of the reference surface during the deformations. So now we already know this. The equations of equilibrium. Applying Low's assumption, the stress-strain relations. First we take the strain displacement relations and the stress and the strain relations for the kth layer in the layered shell defined by like this: sigma x, sigma theta, tau x theta. This is the material description. So this is epsilon x, epsilon theta, gamma x theta. Here the Q11, Q12, Q12. This is the thing. This we can take Ex by 1 minus nu x theta, nu theta x. This is Ex, E theta. This called Young's modulus. Young's modulus. We take this one. So this is the nu is the Poisson ratio. So here Young's modulus, nu is the Poisson ratio, G is the shear modulus. Sigma x and sigma theta are the normal stress components. Tau x theta is the shear stress components. Epsilon x, epsilon theta are the normal stress components. Gamma x theta is the shear stress component. This already we derived it. Now we come to here. This stress resultant and the stress moment resultants, stress couples resultants we can call, that stresses over the shell thickness H are integrated to obtain the force Nij, and the moment resultant Nij are given by this one. So Nx, Nx theta, N theta, Nx theta, Mx, M theta, Mx theta. This is the relation between the moment stress resultants and the forces. These are resultant force, this is the resultant moment. This relation we have to substitute here in 2.4 and 2.5. So we get like this. So this is the thing. We are getting this. So nx n theta, nx theta, mx m theta, mx theta in terms of strain and kappa x kappa theta, tau. Okay. Where aij is defined. This is the a11, a12, a12. This is the aij. Defined. Bij is defined. Dij is defined. What is aij, bij? Aij is the extensional rigidity. Bij is the bending, stretching, coupling rigidities, and Dij is the bending rigidities. And Zk is the distance from mid-surface to the surface of the kth layer. So having farthest Z coordinate. Now this one we have to substitute. Now this Aij, Bij, Dij, then this epsilon x, epsilon theta, these are all given here. Yeah, this the equation 2.2. This also substitute in the equations, and we get the differential equation in terms of the displacement components u, v, and w. U, v, and w. So the each equation, three equations will be there. The three equations will be in terms of u, v, w. So this became as a differential equation in the separable. Now what we do, it consists of the variables x, theta, and t. Now we use a separable method u in the form of like this, u, v, w. You can take u equal to u of x cos n theta e I omega t. V equal to v of x sin n theta e power I omega t. W equal to this. So this is the periodic functions. So it is eligible to substitute in the equation separable form because of cos and sine are the periodic functions. So okay, so it will be you can see that like a Fourier series. No, Fourier series consists of the periodic function sine and cos. Okay, so the same way we have to take this cos sine functions. We have to assume this is a periodic function. It is eligible and it will satisfy the boundary conditions. We have to take in such a way. Okay, where x and theta are the longitudinal and rotational coordinates. Omega is the angular frequency of vibration. T is the time, and n is a circumferential known number. Now, so now we have taken this one and substitute in that. Okay, now we have to take the relation between this structure model and fluid model. Now, the fluid term, how to couple with the structure model. The fluid is assumed to be incompressible, inviscid and quiescent. The velocity potential satisfies the Laplace's equation, and the Laplace equation expressed in the conical coordinate system. It is given in the reference 14. This we are going to take. Where phi is the velocity potential, and therefore what is a Vx, V theta, V alpha. Vx, V theta, V alpha are the components of the fluid velocity. Using the Bernoulli equations, hydrodynamic pressure as follows. P equal to minus rho f dou phi by dou t. Here rho f is the fluid density. The impermeability condition which ensures contact between the shell and the fluid. This condition will satisfy 1 by x dou phi by dou alpha in the wall, dou w by dou t at alpha equal to a in the wall, alpha equal to a. This condition will satisfy. Then method of separation of variables for the velocity potential can be assumed as follows. So phi of x theta alpha t equal to same the separable variable method. We can assume r of alpha phi of x theta t. By plugging this 212 into 211 and together with the radial displacement of the shell, equation 2.7, the function obtained as phi of x theta t equal to dou w by dou t x by r dash of a. Then substituting this equation into 2, the relation becomes like this. Phi equal to r of a by r dash of a dou w by dou t into x. Okay. Then substituting this one into 2.8, the following second order differential equation is obtained like this. We have to solve this differential equation. This becomes like this differential equation, second order differential equation. So this is this is how the equation is. It is a series solution. We can apply the series solution to solve the equation. So here we use the Bessel function. Okay, using the Bessel functions, then we get the solution like this. Phi, we get the solution. Phi of x theta kx dou w by dou t. Then we substitute here where k is this one. Where k is this one. We are taking the terms. So we truncate the terms. We are taking the particular terms series solution from the series solution. This is the terms will come. Hence we substitute there and we get the pressure. So like this. Now the 2.18 we substitute into the equation 1. Equation 1 we have to substitute. Then that equation will be dimensional equation. Now we have to make the non-dimensional parameters. So we can do like this. X equal to x minus a by L, where x between a and b. Lambda equal to omega L root of r naught by a11. This is a frequency parameter. Beta equal to a by b, length ratio. Gamma equal to h by r, a ratio of thickness to radius. Gamma dash is h naught by ratio of the thickness to length. Del k equal to hk by n, the relative layer thickness of the kth. So where hk is the thickness of the kth layer, h is the total thickness of the shell, h naught is the constant thickness. Now by applying this, all these non-dimensional equation, non-dimensionalized terms into that equation, we get like this. L11, L12, L13, L21, L22, L23, L3. We can write in terms of matrix form, matrix UVW. So where what is L11, what is L12, L13, everything is given here. L31, L32, L33. So the fluid terms comes this. Where that S2, S3, S4, that terms, that parameters, all I have given in this. Then what we do here, this term in this term, the first equation, second equation, third equation. In the third equation contains derivatives of third order in U. The form of 2002.2 is not convenient to the solution procedure we propose to adopt because it is the third order, the previous one, the year star, we modified this. It will be in the third order. So what we do, again we modify the equation. When the equations are combined within themselves and modified, the set of equations are derived. And that first of equation 2.20 is differentiated with respect to x and used to eliminate u in the third equation. The modified equation comes like this. This is the modified equation. So under the L31 star, L32 star, so now it becomes the second order equation. So now here, now we need to solve the equation, differential equation. Here it is a closed form solutions not available, so that we adopt the numerical techniques. So in the numerical approximation, here our plan is to adopt this Bickley type spline approximation. This is a spline approximation. So Bickley type splines. The Bickley type splines has a chain of lower order approximation that has the ability to provide better accuracy than a global higher order approximation. So Bickley constructed is cubic splines over the mesh are given by this one. So cubic and quintic. This is the cubic spline. Similarly, quintic means two more terms will be there. Two more terms. Where H is the Heaviside step function, demonstrated this. It's a Heaviside step functions. So now the displacement functions are approximated like this: U star, V star, W star. See, this is the cubic. Every interval will be the cubic. This is a cubic, quintic. So H is a Heaviside step function. So N is the number of intervals in the range. In the range of x belongs to 0, 1 is divided. The push points of x equal to xs, S by N are chosen as the knots of the splines as well as the collocation points. So now we use the boundary conditions to this problem: clamped boundary conditions and the clamped free boundary conditions. So imposing the condition that the differential equation given the equation are satisfied by these points, splines at the knots, a set of 3n plus 3 homogeneous equations into 3n plus 11 unknown spline coefficients. So by applying the boundary conditions, gives 8 more equations on spline coefficients. Combining these 8 equations with the earlier 3n plus 3 homogeneous, we get 3n plus 11 homogeneous equation in the same number of unknowns. So now it became as a generalized eigenvalue problem. It comes like this. So M and P are the square matrices, Q is the column matrix of the spline coefficient, lambda is the frequency parameter. Results under discussion. Now, then after applying the spline functions, it became as eigenvalue problem. We use eigenvalue techniques to solve, to analyze the eigenvalues and eigen frequencies, and as well as the displacement functions UVW. Okay. Now we do the numerical calculations, computations, and we found out this is some comparative results we have done. So you can see here that n equal to 1, 2, 3, 10, like this we have taken. So these are all the references we have taken, the present results. So you can see the present result. The present results are a little lower than the other results because due to the method and the application, that assumptions also, the parameter assumptions. Table 1 shows the comparison study of conical shell filled with the fluid. Thickness is we considered a radius, a length, alpha, cone angle, and thickness. The shell is made up of steel having physical properties. The result shows that some values are differ from the past studies. This is due to the use of different shell theory. See, the present results apply Low's first approximation, while Carbo et al. Used Sanders theory. The Kumar and Ganeshan used first order shear deformation theory. Okay. Now analysis to our results. We analyze our results. So analyze the vibration of truncated shell, completely filled with stationary fluid using that two boundary conditions. The effect of fluid on frequencies of the shell with respect to the relative layer thickness, semicone angle, and the length ratio are investigated. The materials we used high strength graphite epoxy, that we write HSG, S-glass epoxy we write SGE, and the PRD 490 epoxy, PRD we write steel ST, and aluminium AL. So you can see the results here. So I can show some results here. First we have do the verification, the variation of frequency parameter with respect to relative layer thickness and the effect of coupling for CC boundary conditions. So you can see here, this is the HSG material, the here ST material, ST aluminium material. We are taking like this. So at delta equal to C, this is the delta, relative thickness. At delta equal to 0 here, delta equal to 0. At delta equal to 1 here, delta equal to 1. It represents the homogeneous material. So we have taken different layers. Here we have taken the 2 layers. We consider 2 layers. The structure is made of 2 layers material. It is a homogeneous. Delta equal to 0, when you substitute, it become the single layer. So HSG means the delta equal to 0 means it becomes the single material SGE. Delta equal to 1 means the single layer, single material HSG, like this. In that case, see, it will say here, this is the thing, this is the thing. What is the dots? Dots represent the BIJ, the coupling term. BIJ is a coupling term. When we BIJ equal to 0, this one. BIJ not equal to 0, this results. So there will be the variation between even the two materials. When it became a single material, the same, the coupling term, whether you neglect or not. But when we neglect the things in between, you see, in between for value of delta equal to 0.2, 0.4, 0.6, the values are different. So this is the thing. This is the first mode, second mode, third mode, lambda. First frequency where second one, third one. So when it become higher, the difference will be very higher. Both layers are present. BIJ neglecting of coupling term. Trends of the curve seem depend on the material of the layers. So this is the thing, material of the layer. So this is HSG, LGE and steel aluminum. You see, steel aluminum, there is no difference. BIJ equal to 0 or not equal to 0. So steel and SGE material. So it is this one is PRD material, I think so. HSG PRD material, correct. See, for steel aluminum combination, neither coupling or neglect. Coupling gives no change in frequency since E by rho ratios are nearly equal for this material and materials are isotropic. For HSG PRD combination, the change are not much affected. The frequency through E by rho ratios are not much different. For these materials and both materials are orthotropic. In contrast, the changes of frequency is more visible for HSG, SGE materials and both are orthotropic. It is because of E by rho ratios are much different for these materials. That is a thing. In the case of ST, SGE materials, the changes of frequencies are also visible. Even E by rho ratios are not much different for this material. It is because of one of the material is orthotropic, another one is isotropic. This is the difference. One is orthotropic, another is the steel is isotropic, SG is the orthotropic material. That's what the difference we can see. Then we come to the variation of effect of the cone angle on frequency parameter for clamped boundary condition. The cone angle, effect of the cone angle. We take the effect of the cone angle. So these are the effect of the cone angle. Frequency decreases as cone increases. The decrease of the values of the frequencies as fast in the range of this 10 to 30. This is very fast. See, you can see the first mode, second mode, third mode. Afterwards, delta M decreases slowly. By fixing other values while taking different delta, the value frequency becomes lower than the when the higher values of delta is taken. So this is the thing. This is a delta equal to 0.4. This is a delta equal to 0.7. As far the different values of n is taking, while other parameters are fixed, the frequencies become higher as the values of n increases. So these are another way. N equal to 2, this is a n equal to 4. These values will increase. So similarly, HSG PRD. The value of frequencies of material combination HSG PRD are lower than the HSG SGE material. This is the HSG PRD material, the combination we are taking. Similarly, the value of frequency of material combination ST SGE are higher than HSG PRD. So ST SGE. These are ST SGE values. We can compare these values. The three different combinations we have taken. The combination ST aluminum material have higher values of frequencies than ST SGE materials as shown in figure. HSG PRD less than HSG SG less than ST SG less than steel aluminum. So we can identify which are the lower, which are the higher. Now,
sorry, doctor.
Yes.
Actually, we are run of time. Maybe you have just
I'm okay. No, it's still maybe 2 minutes. I just finished. Just finished.
Thank you very much, Doctor.
Yeah, 2 minutes, I think. Effect of length ratio on frequency parameter for CC boundary conditions. So this is the effect of frequency parameter on CC boundary conditions. So it's a beta variations we have taken. So these are also beta variations. We find out the frequency parameters, omega m. Okay. Yeah. So this is again clamped free boundary condition. The trend is same as the clamped boundary conditions. All the trends, all the variations are the same. So this is the cone angle. This is the beta length ratio we have taken. Conclusion, that's all. Frequencies increases as relative layer thickness increases. Frequency decreases as cone angle increases. Frequency increases as ratio length of the cone increases. Frequency of CF boundary conditions have lower value than the CC boundary conditions. So these are all the references. Okay, thank you. Thank you so much.
Thank you very much, Doctor, for the great talk. And let us now proceed to the question. Anyone have some questions? Go ahead, please.
Thank you, Dr. KKV, for talking to us. You have mentioned in the conclusion part that frequency increase with the cone angle increment. So
yes.
Is there any specific reason behind this?
Frequency increases when cone angle decreases.
Yes.
Yeah. Frequency decreases when cone angle increases. Yes, because of when cone angle increases, it become wide, no? It become wide. So frequency will decrease. The behavior, vibrational behavior will decrease.
Okay. Thank you, Doctor. Yeah. Thank you for your answers. Thank you.
Yeah. Thank you so much.
Assalamu alaikum and good afternoon to everyone. Thank you very much, Dr. KK Vishwanath, for your nice presentation. I have just a simple query or a simple question regarding the prison fluid you use. So what specific type of fluid you have used here,
No, the specific type of fluid we assumed you can see here. Wait.
Like we have different types of Newtonian and non-Newtonian fluids.
No, this is our assumption is wait, I will tell you. Quiescent fluid we call it. So here we have assumed that rho is the some value we have taken from the references. Yeah, this rho f, no? This rho f we have taken some value, sir. Some value from the reference. We have not mentioned what is a particular fluid.
Yeah. This is my question. Maybe this is not important in this problem, that what specific type of fluid is used for this problem. But maybe like in future study, maybe this is just my observation. If we can fix one specific type of the fluid, maybe Newtonian and non-Newtonian, or maybe like these days many people are using nanofluids and hybrid nanofluids, etc. Yeah, maybe like for future consideration. Thank you very much. Thank you.
We have given more importance to the structures problem. So fluid, just we have taken the fluid model and we have given from the reference we have given some value, some density of the fluid. So in future for further problems, definitely we will analyze different fluids. Surely. Yeah,
Thank
sure.
you.
Thank you for your these suggestions. Okay.
Welcome.
Yeah.
Thank you very much, Doctor. Any more questions?
Yes.
Okay. Okay, go ahead, please.
Hello?
Any questions?
No questions.
Okay. Okay, now we will proceed to the fourth speaker, Dr. Elias Khan.
Sure.
Okay, he is associated professor at Al-Majma' University in Saudi Arabia. He received the PhD degree in applied mathematics from the University of Technology Malaysia in 2012.
Sorry, I there was a problem in my speaker. Yes. I'm sorry, I can't.
Yes, Dr. Khan, you are welcome to start.
Yeah, thank you very much. First of all, I'm grateful to the whole team of this second international webinar on science development in ecosystem in KSA. And I'm grateful and thankful to Dr. Noha Al-Jabbar and also to Dr. Gulbahar Ashik for inviting me for the second time in this webinar series. So I'm grateful to all of you and especially to the moderator of this session, Dr. Hanan. I hope I will be invited inshallah in future again and again, and I will share my views in my presentation inshallah. So for the today talk, as I mentioned in my written here, the title is Mathematical Modeling and Simulation of Nanofluids, including Nanomaterials. We know that nanomaterials these days, they are the people, the researcher, they are using in different types of problem. Nanomaterial these days, not only the researcher from the physics or from specifically mechanical engineering or the heat transfer, but from many other areas of science and technology, the people are using nanomaterial for different type of purposes. Here in mathematical, in the mathematical aspects, we are using nanomaterials because like I asked from also from Dr. Vishwanath about the fluid. So when we consider a fluid, then we want to enhance the thermal performance of that specific type of fluid, then we use nanomaterial. We include the suspension of nanomaterial in the base fluid, and we are making nanofluid in this nanofluid, which is the newly developed nanofluid. This gave us a better thermal performance as compared to the regular fluid. So therefore, we will do the mathematical modeling, and then we use some mathematical solutions, and then we will do the simulation. So before this, I'm sorry why it is not coming back. Presentation. Okay, why this? I'm sorry, the slide is not coming down.
Dr. Sir, please click next button down on your slides. Go to next. It will come automatically, please.
Next button. Oh, I'm sorry for. Can I, Dr. Gulbahar, can I share this again? File.
Yes, you can share again, please. Try again, doctor. We are waiting.
Yeah, I'm sorry for the problem.
Can you please send your presentation to Dr. Ashik?
Yes. Okay, now this is open, but I don't know why there is no next button. Dr. Gulbahar, I'm sending you. Just 1 minute. I'm sorry for that.
Send to me, please.
Yes, I sent it to you. Like, yes, Dr. Gulbahar, I'm sorry if you can help me.
Sorry, I was just signed in from my mobile. Now I am using my laptop and
Okay.
I will share with you soon. Just give me 1 minute, please.
Bismillahirrahmanirrahim. Do you want to show the dialogue again? Continue. How to go to the next slide? There is
Dr. Rahman, can you please share your email address? Here I have a problem with the laptop. Can you share your email address?
I.said@mu.edu.sa.
Trying to open now, but I am facing problem.
It is uploaded, but the next slide, there is no option to go to the next slide. I'm sorry for.
Dr. 1 minute, Dr.
Dr. Khan, it's
Yes.
Dr. Iman with you. Dr. Khan, can you please forward to me your presentation?
Okay, okay. You
Just write my
just
email in the chat box.
okay.
I share it for you, okay?
Let me. In the chat box. Send to your email, doctor. I sent it to your email, doctor. Dr. Faiza.
Yes, we will check, doctor.
Okay.
Dr. Khan?
Yes.
I just sent you my email. Can you please send your presentation?
I sent it to you, doctor. I sent it to you by email.
We didn't receive it, unfortunately. So could you please send it to the email that I just sent it now?
Yeah, I sent it to this email, ISMASSOUDI.
We didn't receive it. So I just sent you email, NALJABER.
Okay, just wait a minute.
Can you see Dr. Khan?
Yes. Thank you very much, Dr. Gulbahar.
Please go ahead.
Okay, I'm sorry. So I'm sorry for the trouble. I'm sorry for the inconvenience. So we will divide this the presentation in the following section. The first we will introduce. We will have introduction, background of this work, problem statement, objective and scope of the study, and then significance of the study. And then we have some proposed problem, a specific problem, and then methodology with the results. Expected finding in conclusion. Yes, the next slide, Dr. Gulba. Okay, so we have I said in the beginning that we in the fluid dynamics we have generally two types of the fluids. One is Newtonian fluid and the other is non-Newtonian fluid. So some fluid we put them in the category of Newtonian fluid like water, kerosene, etc. And some of them we put in the category of non-Newtonian fluid. And similarly, for Newtonian fluid, we have specific mathematical model, and then for the non-Newtonian fluid, we have also a separate mathematical model. So next. Yeah, the example of Newtonian fluids are like glycerine, water, air, kerosene oil, alcohol, etc., thin motor oil. These are all the example of Newtonian fluid. And for non-Newtonian fluid, in the next slide, we have example of non-Newtonian fluid. Yes, next. Dr. Gulbahar, next slide. Yes, these are the example of non-Newtonian fluid, including ketchup, paint, glues, honey, hydrocarbons, printing ink. The hydrocarbons are actually, these are made from hydrogen and carbons. Is a mixture in it. They are used in gas, in petroleum. So these are all example of non-Newtonian fluids. Like we have different example of Newtonian fluid and non-Newtonian fluid. Similarly, we have different equations for them. So in this specific presentation, we have considered one type of this this fluid called Brickman type fluid. And this Brickman type fluid we consider as a Newtonian fluid, but this is a very specific model because this fluid we model in only for the porous material, for the porous medium. For example, we have sand, clay, rocks. All these are the porous material, and we use this mathematical model for Brickman type fluid. Yes, next, Dr. Gulbahar. In this diagram, we can see these are the different material, and we use in the mathematical modeling for such type of material Brickman type fluid. Is a reference we can see from this paper. Yes, Dr. Next. A nanofluid is the main concern or the main topic of this presentation is about nanofluids. So nanofluids are actually the suspension of regular fluid like water, oil, alcohol, acetone, ethylene, etc. with the nano-sized particle embedded in the base fluid, dissolved in the base fluid. And there can be different types of the nanomaterials. The nanomaterials are also in various types. And in this specific presentation, we have used carbon nanotubes. Carbon nanotubes, or we simply call them CNTs. They are in cylinder form, made of cylindrical form from one layer or more layers. And the diameters are typically from 0.8 to 2 nanometer for single wall carbon nanotube, and for multiple wall carbon nanotube, it is from 5 to 20. So in this specific presentation, we have used CNTs, multiple wall carbon nanotubes, and single wall carbon nanotubes. These are different processes in we can see from the literature or from the online sources that how we can make different types of nanofluids by adding a nanoparticle in a base fluid. Next, Dr. Gulbahar. Yes, go next. Yes, next. These are all different types of nanofluids. Application of nanofluids, we can have application of nanotubes and nanofluids in different disciplines. We can use them in engineering, we can use them in medical as well. Like, for example, if we talk particularly about the carbon nanotubes, then we use them in drug delivery, we use them in microbial therapy, we use them in safety concerns, and we use them in medical devices and plants. So nano material or nanofluid, we have their application in various fields, like you can see here in agriculture, in microchips, etc. Yeah, these are different applications. Dr. Gulbahar, go next. And drug delivery. Yes, next. In solar energy, we use nanofluid for in this process. Yes, next, Dr. Gulbahar. In solar collector. And now we specifically talking here about or discussing about the nano material, but we are considering here a single type of nanomaterial in one base fluid. These nanomaterial we can also increase, like we can use two different type of nanomaterial in the same base fluid. We can also, they are called hybrid nanofluid. In other way, we do the hybridization of these two different types of nanomaterial with the same base fluid. And we can also increase their number, like we can use three types of nanomaterial in the same base fluid, in one base fluid, 4 types and 5 types. So until now in the literature, the researchers, they have used 10 nanofluid, like they have used 3 different type of nanomaterial in the same base fluid. So like we can use here aluminium, silicon, in water, in copper, and all other these different types of nanomaterial in same base fluid to make a hybridized nanofluid. Next, Dr. Gulbahar. Next. Yes, as I said, this nanomaterial, the nanofluid idea in the previous slide, it was written that this was introduced by Choi in 1995. And he noticed this, that adding nanomaterial, the heat transfer increases, the heat transfer enhances. So therefore, in many these days, in many heat transfer problem, either they are from mathematics side or from the thermal engineering, the researcher, they are trying to add nanomaterial for heat transfer enhancement. And they have different type of application, like in nuclear plant, combustion, gas turbines, propulsion devices, aircraft, missile, etc. Yes, and these are different types of modes of heat transfer. In this problem, we will use convection, or we call it free convection. And in this, we will use convection, and then in convection, we will particularly use a free convection for the heat transfer. Yes, next, Dr. Gulbahar. Yes, and these are the highlights. As I mentioned that in this presentation, this was general background of the nanofluids in the heat transfer. Now from here, we will continue about the application of nanofluid for this particular problem, like impact of frictional derivative on convection flow of Brickman type C-increase nanofluid with rainfall temperature. Okay, here, just 1 minute, Dr. Gulbahar, if you go back to the previous slides. Yeah, just to explain about the title. Usually in fluid dynamics problem, we use classical derivative. Like the real world problem, mostly they are, just like in the last talk by Professor KK, the physical problem are mostly in the universe, we model them in terms of differential equation, either partial differential equation or ordinary differential equation. But because of the various factors to be included, we mostly use partial differential equation. So in the literature, the people are using the classical derivatives. But here in this work, we have used fractional derivatives, like if the order of the differential equation is not integer, is not natural number, like not 1, 2, 3, 4. If the order of fractional derivative is between 0 and 1, then how we can solve that particular type of fractional differential equation. And this gives the research area which is called frictional derivative. In these days, many people, they are working on frictional derivative, but in the idea of frictional derivative, especially the new definition of frictional derivative, me and my group, alhamdulillah, we have published various and many articles in the literature on the application of frictional derivative for a nanofluid problem. So we will use frictional derivative, and we will consider here next convection, which is called free convection, and we will use Brickman type fluid. So the abstract, we will discuss about the abstract, and these are the different section, the assumption, like in the previous presentation, Dr. KK, he also in his problem mentioned some assumption. So in the fluid problem, we cannot do complete modeling without assumption or supposition. Otherwise, we will get a differential equation which will be highly nonlinear. Therefore, we have considered these points in our modeling, that the flow is incompressible, the fluid is frictional Brickman type fluid. We use here the particular definition of frictional derivative, because in literature there are various definition for frictional derivative. We use here the Caputo-Fabrizio frictional derivative. And then we will model the problem. First, we will find the exact solution, and then we will use some software for the simulation problem. Yeah, and then we will plot the result. Next, yes. This is geometry of the problem, the physical model of the problem. Here we can see this is we have considered vertical plate, and the fluid is moving. And this is in a vertical infinite plate, and the fluid is moving about the fluid is moving about the plate. Sorry, the fluid is about the plate, and this fluid consists single wall carbon nanotube and multiple wall carbon nanotube. This one, the upper layer, if we can see here, this represents momentum boundary layer. And the one, the last one, sorry, the down one, it is thermal boundary layer. Okay, these conditions are very important. The boundary condition, just 1 minute, Dr. Gulbahar. This, the vertical plate which we have considered, this plate is oscillating with a cosine type of oscillation, and in this plate we have considered the temperature net constant, but it is variable, RAM temperature. RAM temperature means for certain portions time there is a variation, and then it remains constant. And we have considered the medium as a porous, and the fluid is moving about this plate. And the fluid away from the plate, we have considered the velocity is 0, and the quotient of the fluid temperature away from the plate, it is T infinity. Yes, next. Okay, so this is a governing equation. This equation 1, 2, under condition 3 and 4, we derive from the Navier-Stokes equation after many steps. So here, this beta star which is written here, this is the Brickman type parameter. If we put this Brickman type parameter equal to 0, then this model will reduce to the regular viscous fluid. The fluid will be not Brickman type fluid. And here, this term, the last term on the right hand side, this is the term which represents free convection, and this term is free convection induces because of the buoyancy force. And equation 2 is just the temperature equation with these initial condition. When the time is 0, velocity is 0, and when the time is 0, temperature is T infinity. And here the velocity, if we take with the sudden jerk, the motion, if we take the sudden jerk, then at boundary the velocity is U0, and here the temperature is RAM temperature. Yes, Dr. Gulbahar. Okay, here in this table we will use this thermophysical relationship for a nanofluid with the regular fluid. This is the density, the kinematic viscosity, and all these, the specific heat, the thermal conductivity, These expression shows how these thermophysical property of nanofluid and regular fluid are connected with each other. For the nanofluid, we will find, and for the base fluid, we already will have these properties. Yes. And here, in this before equation 5, we use these dimensionless variables, okay, dimensionless parameter or variables or quantities to transform the previous equation into dimensionless form, and then we model in terms of frictional derivative. And this frictional derivative we apply on time only. So here you can see this is d alpha dtu. This alpha range is between 0 and 1. So the frictional model corresponding to the previous model, the classical model, the corresponding frictional model is 5, 6, and the initial condition in transform form given by equation 7 with imposed condition, boundary condition in equation 8. Yes, Dr. Gulbahar. Now, and these are the constant appearing during the calculation. So in equation number 10 and 9, this is the specific definition of Caputo-Fibrizio frictional derivative. Okay, so we will use this definition 9 to solve the previous governing equation. Yes, next, Dr. Gulbahar. By using Laplace transform method, yes. So we get for temperature, because the velocity equation in the previous, this is a isolated, but isolated equation, and the temperature, the velocity equation is coupled with the temperature equation. So first we will find the solution for the temperature, and then we will use this solution in velocity to find the solution for the velocity. So for the temperature corresponding to the ramp situation, the solution is given by 11, and the corresponding solution for velocity is given by 12. With these constant, this θ1 ramp, it is equal to this integral, because the solution, they are coming in terms of complicated integrals. So therefore we have arranged them in for the simplicity, in terms of equation 11, 12 with the corresponding quantities in equation 14. Yes, Dr. Gulbahar, next. Okay, these are the solution, okay, equation 15, 16, 17, this completely mathematical solution. So we obtain this solution by using the Laplace transform, and after several mathematical calculi, we reach to this equation. Now we will plot this equation by using software. Yes, Dr. Gulbahar, next. Yeah, similarly, solution for the velocity profile are given here with these constant. Yes, Dr. Gulbahar. Now, as I mentioned in the previous slide, we obtained the exact solution by using integral transform method known as Laplace transform method. Now, this solution we will plot by using here we have used MathCAD software, which we use usually for solving our problem. We can do this by Mathematica, by MATLAB also, and we have computed the results. Here, this dotted line shows here, this is for ramp temperature, and the solid line, it is for isothermal temperature. Isothermal temperature means temperature is constant at the boundary. Ramp temperature means the temperature depends on time at the boundary. So we have plotted the graph for the velocity and the temperature for both cases, ramp and isothermal, and we can see here the ramp temperature here. This figure 1 is for temperature, which is in dimensionless form, theta, depends on y and t, the space variable y and the time t. Here the temperature, we can see, just 1 minute, Dr. Gulbahar, we can see this, the temperature for ramp, for isothermal case is higher than the ramp situation, okay, because of the ramp phenomena, the ramp nature of the temperature, the constant temperature is higher, and the ramp temperature is lower thermal boundary layer and approaches to the x-axis or the horizontal axis faster than the constant temperature. So in this whole graph, we have compared for ramp and isothermal temperature, the velocity as well as the temperature. Then Dr. Gulbahar, next slide. Yes, just 1 minute. Here, in this, we have compared the temperature and velocity for single wall carbon nanotube and for multiple wall carbon nanotube. For single wall carbon nanotube, we can see here for single multiple wall carbon nanotube, this down one, and for the single carbon nanotube is the top one. So by increasing the RAM temperature, when the RAM in case of the RAM temperature, the thermal boundary layer is shorter, and the case of isothermal, the thermal boundary layer is larger compared to the ramp one for both multiple wall carbon nanotube and for a single wall carbon nanotube. Yes, Dr. Gulbahar. Similarly for the velocity. Yes. So thank you very much for listening. And if you have any question or any suggestion, kindly, I'm waiting for your question and answer or suggestion.
Thank you very much, Dr. Khan, for the nice talk. And if you have any questions.
Yes, Dr. Yasin, thank you very much for the nice presentation. I want to ask that which kind of fluid you have used, either Newtonian or non-Newtonian fluid?
Thank you very much, Dr. Gulbahar, and for helping me in in this problem. And I'm sorry for that interruption. In this problem, because as I mentioned, this Brickman type nanofluid is of Newtonian nature, so I have used water as a base fluid, and I have added multiple wall carbon nanotube and single wall carbon nanotube in water. So the mixture is the water and nanomaterial, single wall carbon nanotube and multiple carbon nanotube. Yes, Dr. Gulbahar.
Thank you. And why most of the researchers use Newtonian fluid and they don't want to go toward the non-Newtonian side? What is the reason behind this, Dr. Khan?
The Newtonian fluid actually, all the Groningen equation we derive from the Weierstrass equation. So for Newtonian fluid, these equations are simpler as compared to non-Newtonian fluids. This is one of the reasons that the people, they first try for the Newtonian fluid and then they go for non-Newtonian fluid, because in non-Newtonian fluid we have additional non-Newtonian effects. Because of those non-Newtonian effects, we get more complicated partial differential equation, and then it is not easy to handle them, particularly for finding exact solution, and also even not numerically. Therefore, many researchers, they are focusing on Newtonian fluid and less are working on non-Newtonian fluid.
Thank you very much, Dr. Khan, for your answer. Thank you.
Thank you very much, Doctor, again. And now we move to the last speaker today. We welcome Dr. Yvonne Munjir. She is postdoctoral researcher at the National University of Engineering in Peru. She is a chemist, and she has experience in thermal properties, synthesis of nanoparticles and materials for environmentally friendly energy uses. She was a postdoctoral researcher at the University of Sao Paulo, Brazil, since 2018 until 2020, and the University of Quebec in Montreal, Canada, from 2019 to 2020. And her topic today is about lithium-ion batteries, alternative electrodes, and electrolytes. Hello, Dr. Yvonne. Dr. Yvonne, can you hear us, please?
Can you hear us, please?
Dr. Yvonne, you are welcome to start your presentation.
Can you listen to us, Dr. Yvonne, please? Hello, please start your presentation.
Can you hear us, Dr. Yvonne? Hello?
Dr. Yvonne, your sound is very low. Please check your speaker mic.
Dr. Yvonne, please turn on your microphone, please.
Okay, please change your mic. Yes, we received chat from you. If you can hear to us, please change your mic. We are waiting. Thank you, Dr. Yvonne. Still your voice is lagging. You can hear us? Please, we can't hear you.
Your voice is very low, doctor.
Still, we can't hear you, Dr. Yvonne, clearly. Can you please increase the volume or change your mic, please? Change the slide on your laptop. We are hearing you. You can speak here.
Okay, perfect. Can you hear me?
Yes, we can hear you. Yes, we can hear you. Please speak.
Yes, you can start, doctor.
Excuse me.
Yes.
A little, because I'm gonna share my screen.
Okay, share your screen and read the slides. Yes.
Okay, I'm so sorry. We are going to talk about some results that we have obtained during my postdoctoral research at the University of Quebec in Montreal and also at the University of Sao Paulo, Brazil. Currently, I am postdoctoral researcher at the University of the National Engineering University of Peru, but we are going to talk about some of my previous results. As it is well known, combustion fossil fuels is producing so much problems to the atmosphere, mainly because of the harmful gases that are released. So consequently, there are a very huge interest in alternative storage systems, such as lithium-ion batteries. Change the position a little bit because I part of the presentation. So here in this image, you can see a Tesla Model 3. It's one of the commercial electric vehicles that are available right now. However, one of the main reasons why electrical vehicles are not massively used nowadays is because of the lithium-ion batteries technology. Mainly because it has a high price, and also because the material that forms the cathode and the anode, the battery, requires higher specific capacity. Here we have some images about the structure of a Tesla vehicle. In the lower part of the car, you can have several hundred of small batteries. Each of them has a anode. Usually it's made of graphite. The cathode usually is made of transition metal oxide, one called MCA. And also in the it is common to find an electrolyte. And we are going to talk about different material for anodes and also for electrolyte. Here we have a representation of what's happening in a car while it's charging. So you can see that the lithium ion and from the cathode, here is like a pyramid, from the cathode to the anode, which is in the right side. Usually it's made of graphite. You can see that the lithium ion moves, and also the electron. When we are running, in this case, we have the opposite, and the lithium ion are moved from the anode through the cathode side. Right now, more than 90% of the market is mainly the market of anodes or negative electrodes is based on graphite. As you can see here, the silicon, which is an alternative material, occupies only 2%. And that is important because if we see here the specific capacity of the graphite, it's around 10 times lower than silicon. But to change the technology to silicon is not quite easy, mainly because the volume expansion of silicon, which is around 300% in comparison to graphite, which is 13%. So this is producing some problems, the silicon anodes. As you can see here, we have a schematic representation of what is happening in the silicon when the lithium ions are going into the particles. So the process of charge, so that the particle increase the size, and then during the opposite procedure, during the discharge, so the lithium goes out, but some of the interface is represented here as a gray line. And then if you have this process several times, at the end, it's possible to have a very huge interface. So that you can see in gray. And it's producing too much problem because it's affecting the lithium ion mobility and also the electron mobility. Consequently, there are currently a very huge interest in solve this problem. So we can try to solve this problem using silicon of nanoparticle size. So, but the problem is related to the price because they are very expensive. Also, we can try to solve the problem modifying the electrolyte. Why? Because if we modify the electrolyte, it's possible to reduce the amount of the solid electrolyte formed of this gray layer. So this is one of the alternatives, and also it's possible to change the anodes, and this is one of the objectives of this research. So we explore silicon oxycarbide because currently in Tesla, it says that they are using less than 5% of silicon. So it means that the technology is still at the beginning and too much research is needed. So silicon oxide carbide is a family of the silicon oxide, it's a member of the silicon oxide family. And we are interested in this kind of materials because it has several sites for lithium insertion. As you can see here at the left side, so the silicon oxide carbide has a carbon structure, and also it has some OH and some different silicon oxide structures. So they are like 5 different possible structures. So each of them can storage silicon, and this is why this kind of technology is very important. We have published this research last year, and it's a collaboration between Brazil, Canada, Finland, and Peru. And we were interested to have a very easy procedure for the synthesis of this material. So, as I mentioned, some of these tetrahedral units are very attractive, but some of them not, because they are irreversible. So it means that they uptake the lithium, but the lithium is not released anymore. So in terms of battery performance, that is not a desirable situation. We need reversible phases. So we propose to use this precursor, which is not usually used in this kind of synthesis. This is the first time that it's used. Because it's quite common, but for the modification of nanoparticle and for other applications, but not for lithium-ion battery. And the reason why we were interested in this is because we have here a tetrahedral structure in which silicon is bonded to 3 oxygen and a carbon. And this carbon is bonded to a amine group. So it means that if we use this compound, we can have in addition to the oxygen carbide, we can have an amine or a nitrogen source inside the structure. And this is very interesting because it can improve the electrical conductivity and some electrochemical properties. The synthesis is quite easy. We only use glycerol, sodium citrate, and this precursor called APTEs. And we use a oil bath. And the reaction is nitrogen, and it has 2 steps, heating at 100 degrees, and then in the second day, heating for 1 hour at 180 degrees. Then dialysis of filtration, we pyrolyze the powder obtained, and at the end, we are going to have this black powder. And we decided to use a variable of this research, the molar ratio. So it means the amount of citrate and IPTs that we add to the reaction. So because we wanted to change the silicon oxycarbide structure and respect to the carbon structure. So this was the objective of these variables. Here we have some results about the morphology. These are set micrographs in which we compare both the materials. At the left, you can see some small particles, while in the right you can see huge particles, and they are amorphous, as you can see here in this small square. So they are amorphous, and also the surface area is higher in the sphere-like particles compared to the huge particles. So also we did some physicochemical characterization. Here we have some Raman and some Raman spectra and the TRX of the sample synthesized. You can see here the TRX of an amorphous material. And also here in B, the Raman spectra show us that we have a small amount of silicon amorphous, which can be seen around 500. And also we have some differences in terms of the disorder of the carbon structure. So the sample is fair. It has a little bit more disorder. And also here we have another characterization. This is a solid NMR in which we confirm that we have different tetrahedral structure. And in terms of composition, this TGA show us some small differences, around 5%. And if we correlate this result with the elemental analysis, we see that this elemental analysis was specific for ceramic. We have some differences in terms of the carbon and also in terms of the oxygen. During the XPS analysis, we see different pyrolytic, pyridinic, and graphitic structure. So it means that we were able to insert some nitrogen structure into the material, which was one of the goals. And also we confirmed that we have different oxycarbide structures. One of the explanations of what could happen here is based on these papers. They said that when we have a amine group in a citrate, citric acid, it's possible to produce some rings that has inside nitrogen atoms, and this could be one of the reasons why we have this structure. And as we see here, we confirm that this is the percentage of each species, of each nitrogen species. We tested the material as anodes or negative electrodes in a clock box. This is the schematic representation of a coin cell, in which we have here inside the electrode that we synthesized. And we did that inside a glove box because we need an inner atmosphere. Some of the electrochemical results are shown here, this slide. So I imagine that some of you are not quite expert in this kind of technique, so I'm gonna try to explain a little bit, but if you have any question, just ask me. So here in this A image, we have a specific delegation. So as I told you before, so graphite has around 372, And this material has around, one of the samples has around 600. So it means that we have a very good performance compared to graphite in one of the samples in that spheres-like particles. And also in the B graph, we have a test about the stability of the samples. And we observed some differences, but when we return to the initial condition at 1,000 cycles, we have almost the same initial values. So it means that the material is able to recover the initial properties, which is very interesting in electrochemistry. So this is a summary. This is the conclusion of the paper. So in which we can see that we were able to form an interesting material, and they were used as non-phosphorylated ion batteries. Also, I'm going to talk you about some of these results, which are about the synthesis of ionic liquids and characterization of them, and we use them as electrolytes for anodes. Again, this is a paper.
We cannot hear you. Can you please speak loud?
Dr. Yvonne, we couldn't hear you.
Doctor, I am contacting again. Her contact has vanished. Now I am contacting. Can you, Dr. Yvonne? Can you please speak, Dr. Yvonne? I am contacting on phone. She's on call. She muted the call. Yes, can you speak, please? Please don't press the mute button. We can't hear you. Can you please speak? We can't hear you. Yes. Yes, we can hear you. Thank you. Please.
Okay. So sorry. I'm gonna continue. So here we have, you can see the prototype of the coin cell. It's the way that we tested the material synthesized, and in this case, the electrolytes. The research about electrolytes is quite important because some of the problems that are related to lithium-ion batteries are because of the electrolyte. Sometimes you see some news about fire explosion or some problems, and it's mainly because of the electrolyte. So this is the reason why right now the research about these electrolytes are quite interesting, because it's needed to explore new electrolytes in order to replace the organic solvents, which are very that are the main producer of that fire. So one option is the ionic liquids, because as you can see here in this slide, compared to organic solvent, which is the current technology, ionic liquids are not flammable, and also as we can synthesize them in the lab, so it's possible to change the properties, which is very interesting. In fact, this is the main objective of this paper. We designed a new ionic liquid. There are different cations and ions, but we are going to talk about some called phosphonium. And here we have in blue some of the anions that we use. I know if some of you have some question about structure or something like that, just let me know. I'm not going to talk too much about this, but just I want to say that we characterize them, and they are new. This is the first time that they were synthesized and applied as electrolyte in lithium-ion batteries. And we also compare them with a commercial organic solvent mixture, which is called EC and EC. It's a carbonate material, carbonate electrolyte. And here we have some results about viscosity, density, and conductivity. Sorry, it is not electrical, it's conductivity. And here we see that in terms of viscosity, the results are higher for ionic liquids compared to organic solvent, which is in black here, black square. Also density, we see that the ionic liquid has higher density compared to this square, this black square, which is for the organic solvent. And also the conductivity, we have also a higher conductivity for organic solvent compared with ionic liquids. So it means that ionic liquid seems to have worse properties compared to the organic solvent. And that is one of the most important questions to solve, because this is one of the reasons they are not massively used right now. However, even if we have that inferior properties, lower properties, we tested them as electrolyte in lithium-ion batteries, and we have the results here in this slide. You can see here at the A side, in the upper, we have the organic solvent response. In this line called delegation charge, we see that we reach like a 3,000, sorry, and this is for the commercial organic solvent. And also a similar value was obtained for ionic liquids, which are in red. That you can see here in the X axis, we have around 3,000. So it means that even if they have worse properties, they are working very well as electrolytes. And also in D, you see the delegation capacity and as a function of cycle number. And after 30 cycles, which is at the end of this graph, the performance of the delegation capacity of ionic liquids are quite similar to organic solvent. So it means that they are working similarly. Of course, we need to explore more about these electrolytes. So we are right now finishing a paper in which we explore like 1,000 cycles to see the performance and the difference between these two electrolytes. But it seems that they are working very well. So as a conclusion, we can see here that we were able to synthesize new ionic liquids, and they are working well as electrolytes in lithium-ion batteries. I just want to say to you, thank you for your time, for this nice opportunity. Thank you to the UCAN and the University of Sao Paulo in Brazil. Any question?
Thank you very much, Dr. Yvonne, for being with us today. And if there is any question, please.
Yes, Dr. Yvonne, thank you very much for telling us about the lithium-ion batteries. What is the future of lithium-ion batteries? Can you please tell us more about this?
Yes, of course. So right now, I think that in most countries, so this is one of the most important research. Right now, they are focusing on finding new materials for cathodes to replace some of them. For example, that I use cobalt because it's quite toxic, and there are some problems in the mine for the acquisition of the materials. They are trying to explore new materials, easy to find, easy to get it. And also in the anode side, as I mentioned here, there are some problems with silicon, so another other field. And the electrolyte, as I mentioned, they are explosive, so we need to explore more about other alternatives. So I think that other countries are interested in how to recycle these batteries, and I think that this is a very, very interesting topic right now.
Thank you very much, Dr. Ivone, for your reply, please.
Thank you.
Thank you, Dr.
Yes,
Ivone.
Dr. Noah.
Any more questions? Okay, thank you very much, Dr. Ivone. And at the end, we thank all the speakers again for their effort to get their presentation out in a well-organized and valuable way, and for contributing to enriching the scientific research in our university. And we really immensely appreciate your valuable talks. Thank you very much. And also for all of you for listening. Thank you very much, and have a very nice and wonderful evening. Thank you. Bye-bye.
Thank you, Dr. Noah. Thank you very much.
Thank you very much. Have a good day. Bye. Assalamu alaikum.
Wa alaikum salam.